Let's wait a couple more minutes and then we start for the afternoon session. Apparently, to motivate your asking question and actually talking, this morning I was here the last hour and a half, you were very silent. This is not good. So we bought a lot more chocolates. Look at this. We have 3 bags of chocolate and also some local sweets. I think they are Ruscos, I don't know. I tried one and it was delicious, so they're good. What do you call them? Someone local here?
Hojaldrina.
But they are not for vegetarian people. So if you are a vegetarian, please ask and you get chocolate.
We have enough now, so Mark can hit you with an attack.
So now Mark has, Patrick has had many questions on your talk, right? So get ready then.
Right.
Yeah.
And actually you may also have tomatoes because, as I said, this will be a bit more controversial and less, I would say, established materials. So if you disagree, maybe you can manifest yourself by sending tomatoes and we'll send you sweets.
If you disagree, you get 2 sweets, not 1, 2.
Yeah, right. Okay. Okay. So, well, essentially, I will discuss the issue of the start motion rate and initial mass functions, which have been, let's say, 2 of the pillars of the start motion question and stories for years. And okay, let me first start with this. So this cycle you probably discussed already from galaxy down to star, if you want. So that's part of the origin of the complexity of this field. And you have to cover something like 10 orders of magnitude in scales and 20 orders of magnitude in density. And I'd like to pose questions associated to this. So the first one, I place it around there. Okay, it's also always a bit, a bit tentative, but still, the star formation rate is like a semi-large scale-ish issue, and so there have been this question about magnetic field turbulence and feedback, which have been discussed before. Then I will place the IMF sort of here. But as I would say, actually, I think it's a truly multi-scale process. So it's more like it goes from something like here down to almost AU scale, I would say. And then, of course, this and so on, which are less important for this question. And then finally, star formation, as we all know, and this question of the IMF is, of course, fundamental because of this feedback on the large scales. And understanding whether feedback make it all is part of the debate that I will try to address. Okay, so here's my plan. First, I discuss the star formation rate and I discuss the principle of analytical models. Then present some success and also failure of the sort of self-regulated feedback ISM. Also, some team may have more success be more successful than what we have been. And then discuss my opinion, at least, the need for large-scale turbulence on top of feedback, which is, I would say, important. And then for the IMF, I will split it in 2, essentially the power law of the IMF, okay, and the question of the peak. Okay, so the star formation rates, there are 2 fundamental things to address. The first is the sort of inefficiency of star formation, which is there for like 1 century, half a century. Essentially, if you compute with very simple arguments, the mass divided by 2 time, you find the star formation rate, which is typically 2 orders of magnitudes larger than what's measured. So there is something fundamentally missing there. And the question is what is it? The second pillar is the Schmidt-Chemical relations. If you look at this star formation rate as a function of current density, there is this 1.4, which can be probably on the about, say around 1, okay, plus or minus something. And so you have this current density as a function of star formation rate, and I find it remarkable that, you know, over something like 3 orders of magnitude, roughly, you get, there is some dispersion, but still, I mean, scientifically speaking, it's a pretty convincing correlation. So those are the two really big things we would like to understand. Okay, so 7 models have been proposed to understand the star formation rate. They are based very largely on this PDF. So the idea is that you have like a turbulent, supersonic turbulence going on. So you have, you know, series of shocks all over the place, and this creates something like a log normal PDF. Okay? So the log of density and the distribution of points. And so the idea beyond those models is that you pick up one density and you have to integrate over what remains above that density. Of course, this choice of the threshold is actually not innocent at all. It's very important, and in my opinion, that's one of the very weak points of the model at the moment. Actually, we are working on that, but I'm not going to discuss that tomorrow. I hope there will be some published in the publication in the future, but for now, that's where we are. Huh? You pick up a criteria, which is typically genes-based criteria, sonic length-based criteria, and then you integrate. So this gives something like that. You have your density PDF, the mass or the density associated to it. You divide by the free-fall time, and you integrate above the density threshold. Okay? So that gives you the sort of compact formula, which are called sometimes the multi-free-fall star formation rate, because we just introduce the free-fall inside the integral instead of outside. So of course those formulas are very convenient, so we can use them and so on. So, yeah.
How do you determine the threshold?
Yeah, as I said, this threshold is controversial. In my opinion, there is no threshold actually. And if you want to hear my very deep opinion, I don't. This model needs to be revised, but I'm just telling you what is existing. I think there is no reason to have a single threshold. You should perform a multi-scale integrations, which really scale by scale, like a bit like pressure structure actually, determine what is stable at a particular scale, at a given scale, and integrate over. That's essentially a part of the things which are under development. But okay, still, when you compare with observation, I mean, the point that there are always fudge factor, so you can always, you know, that's what has been done here, for example, in this work by Christopher Dart and Arfresen, where they try to determine the best factor that could help reproducing the model, so they get.
Sorry, Patrick. Also, one more question.
Yeah.
Question to that. So what's the origin of this enormous scatter? I mean, what's the main reasons for the scatters in the observations and in the simulation? Is it systematics in the observations, or is it different galaxies?
No, actually, in those particular, that was not galaxies, that was, they were star-forming clumps, actually. So the scatter, I mean, here those are various bench of simulations, so you just have different simulation parameters. In the observation, I'm not sure I can answer. I mean,
Those are
those are
some,
observations.
like on the right-hand panels, there's better fit, and the left-hand panels are clouds to me, the simulations. The right-hand panels, I see a relation. The left-hand panel, I just see clouds, particularly
Well,
on the left.
I mean, those are just the SFR simulation as a function of SFR theory. So it's a way to
Okay.
compare. Yeah, sorry, I've been a bit too quick. It's a bit It was a way to compare the result from simulation and from theory.
Alright.
Yeah, so, and then of course
Remember the
you have to
tutorial
fit
next week
those factors.
for question.
The-
What the students do, so please ask questions, just don't absorb passively.
And so here,
Don't believe a word that he's saying.
yeah. So this may also be like an age issue because of course there is always a snapshot. And actually this is a complication when you, well I'm telling now, I'm using an observational hut, which does not go very well to me because I don't observe at all, but essentially the star formation rate is easier to determine in simulations because you have the whole history, and also because very often you have like a isolated clouds, so you know exactly what's the reservoir that you are dealing with. The observation is much more complicated because as we were discussing a couple of times, actually a cloud is never truly isolated. It's always a continuous, hierarchy of scale. Even molecular clouds are embedded in large-scale H1 filaments. So first, determining exactly what the reservoir is difficult, and B, because of feedback, quickly you start pushing the gas around. If you remember the simulation I was showing this morning, rapidly enough you start decoupling, also maybe because of the mechanisms that proposed, but recently, quickly you start decoupling your stars and your gas, and to decide that, okay, these stars has to be associated to this cloud or this reservoir of mass to determine something like a star formation rate is complicated issue. So that may be part of this, but honestly that's the best I can say. Right, anyway, the purpose here was just to say that those models are not completely, I would say, incorrect, but I think there's still much progress to be made, both for the theory and essentially all those factors here should ideally be determined. Okay, so that's analytical okay, works. So in this type of model, you prescribe the velocity dispersion essentially, or you assume a Mach number, but you don't look at the origin of this Mach number. So there's been a great deal of work. I'm just listing them, but probably not them all, but many of them, essentially doing this. So this is a kiloparsec box, okay, where you have a galactic disk, so you prescribe a gravity version of the field, which is essentially taken from observations. Okay, and you have a self-regulated ISM, so you treat at some specific scale, typically a few parsec, the formation of the star through gravity. So you have the same particles, which sort of accrete continuously material. And when you have accreted sufficient amount of material, so typically 100 solar mass, if you believe in the IMF, the measured IMF, you should have at least one massive star which explode in supernova. So you can track this in the most recent, most advanced model. We actually follow the sync particles, and when the age of the sync particles becomes larger than the age, the estimated age of the massive stars, okay, you put your supernova, and you will also have H2 regions and so on in the most recent. So here essentially you have two equilibrium. One is mechanical between the turbulence and gravity, essentially the turbulence which is due to the supernova in this case, and the other one is an energy equilibrium, so the energy injected by the feedback and dissipated by the turbulence. By the turbulent cascade. All right. So many groups have been doing this with various assumptions, and of course the degree of realism is more. So essentially, what you will find is something like this. If you have no supernova at all, you just get collapse. So catastrophe, you convert all your stars in one free-fall time. Magnetic field does not really help. Supernova help a lot. Actually, so this is the slope that you want to recover, which for this density would be the mean value of the Schmidt chemical relation. So the goal is to have the slope here. And so, and when you have, that's what you have when you have supernova and H2 region. So at the end, you see you find slope, which is approaching this one. It's still maybe here a little bit larger. We'll come back to that later. But in any case, you have done a lot. Okay, because we started from here, and so you reduce it by more than factor 10. So the question as to whether it is compatible or not can be debated, but at least you are getting much closer. I mean, there are possibly a few things missing, like the shear, cosmic rays, and winds are not included. So probably you could probably again a little bit more. Okay, and that's the way essentially the ISM reacts, which is interesting. You see, once you have more feedback, essentially, so you increase a little bit here, but not that much. What is really noticeable is that you actually increase the amount of gas in these regions, which is like the mean density of few cc. So what feedback does, or the way SFR is really regulated in the model, is by allowing the gas to stay in like diffuse form in the galaxy. Okay, it's not that you maintain the dense gas forever and so on. No, it's more the diffuse gas. So you, in a sense, prevent the production of dense gas. Okay, which makes sense also because there is an issue, of course, with the correlation between the dense gas, for instance, and the supernova. Supernova, they come very late, and so to inject actually, akinetic energy in the dense gas from supernova, I think it's very difficult. Yeah.
I might have missed it, but why is there the dip around log n equal to 1 in the density PDF?
Sorry, I'm not sure.
So like,
why is it 5 out?
Oh, the two
yeah,
bits.
yeah.
That's the multi-phase nature of the ISM.
Oh, right.
It's one phase and color phase. Yeah. Okay. So this I would consider is a kind of success. As I said, you can probably discuss whether you get really the exact value, but it's much better. I would say almost there. Probably there if you add a few other things. So I consider this as a success. Where I consider there is a failure is about Schmidt candidates. So typically, when you run a series of simulations by changing the current density, so same things otherwise. Huh? So it turns out that you are doing a good job for Milky Way-like galaxies, but as you go to denser environments, we find that the coefficient is not right. We find that as you go to higher current densities, you are above, significantly above Schmidt candidates. So in our simulation, it seems that the feedback that is included is not able to reproduce Schmidt candidates. And as I said, that's something, there may be some controversy. I will show something at the end. Yes?
So you are comparing the YSO's type, star formation rate, and then gas density to galactic scales, though. Is that a problem that could explain the disagreement?
I mean, myself, I've never determined SFR conservation. What I understood from several is when you are working at a scale which is larger than 100 parsec, you are safe, but whether you are completely safe, I mean,
But your so the simulations are averaged over
Right.
100 parsec.
the simulations are average over 1 kiloparsec.
1
Typically, we
kiloparsec.
took the simulation. But of course, those boxes, they have important limits, and I'm going to precisely discuss some of them right now. So one of the possible issues is that those boxes are completely isolated. By definition, it's self-decoding. Yeah? Okay. Just change it. Okay. So yeah, as I said, those boxes, they are completely isolated, so all the energy comes from the feedback, but it's not a galaxy. In the galaxy, you have not the large scale driving, that could be the spiral patterns, but more generally, you have shear, and if you have large scale instabilities, say gravitational instability, then you have like a cascade, which starts at the full scale of the galaxy and which cascade down. So what I think is missing at the moment is a thorough understanding of the respective amount of energy that comes from the large scales and the one that comes from the small scale. And that's what I'm going to discuss now. So the idea is to, on top of the feedback, to also drive turbulence into those boxes to mimic what could be the result of large-scale driving in a galaxy. So of course it's at the moment it's a bit ad hoc. So, but it's a way, because the problem when you do galaxy simulation is that they are just enormous, and the resolution usually is not as good as what we can do here. Sometimes they can do quite well in the dense gas, but it's not only a matter of solving well the dense gas. If you want to do with turbulence, you must have like a sufficient weighting of your turbulence everywhere. Otherwise, you miss, the bulk ISM turbulence, and this will have consequences on your cascade. Okay, so that's the sort of questions you can play around with when you have both large-scale full galaxy simulation and small boxes where you can have like uniform turbulence or uniform grid, which and high resolutions, which allows you to have less problems of numerical distribution. Okay, so the idea is that we add by hand this sort of driving, and then we can vary the amount of driving that is that we deliver. And the physical idea behind, actually being proposed by Frédéric Bono and Mark, is that you actually tape energy from the rotation itself, for instance, there can be other sources. Okay, and this reservoir of energy will be used to feed the turbulence if you can tape on it. Right? So let's have a look to two simulations. So one without driving, this has a relatively high current density. So here you actually see the sort of catastrophe operating. You see the collapse occurs at a few places, and it's very intense. I mean, you like turn, too much materials in few photons. If you do the same here with the driving, you quickly see a completely different picture. Essentially, you shear apart your large. So you prevent the large collapse. This region is not going to happen just because it's completely shear apart. So you see it would have begun, but because of the large scale motion, it's just dissolving. Okay. So whether or not this is the correct amount of driving can be debated. Okay. I think there is no question that there should be at least some. Whether this sum is making a difference or not, this I don't know. So that's part of the controversy. But I think it's typically the questions that need to be clarified by our community. Okay. We need both. Yeah.
So I'm just wondering how actually the inertial, how you back up this rotational information. How actually this rotational information is stored, because actually these things are moving with this velocity. So actually it's a kind of their they are not, they don't have velocity at all. So you must have gradients, rotational gradients that are inputted from the external regions. Is it? Am I correct or not?
You mean
How do you input this rotation if they already have this rotation? You don't understand. It's like they are.
the idea is that you the picture we have in mind is not so much. I mean, you could have shear. Actually, the best things would be to do both shear and turbulence. So at the moment, we do either shear or turbulence. But what we have in mind here is that this is really you have like a turbulent cascade, which occurs from the very big galactic scale, say kiloparsec or more, down to where it is dissipated. So there is a
turbulence
energy.
would be the driver. Turbulence would be the driver of the.
No, turbulence. The large scale, the driver would be, for instance, the large scale gravitational instability, like the spiral waves. I mean, this has been actually demonstrated. There are papers like Vada et al. In the 2000 something, where they had this. They had just one spiral pattern and showed that the whole galactic disk would become turbulent.
Okay.
What is not easy, that's a bit tricky, is to decipher the two, because once you are doing a full galaxy, by definition you have it. Or maybe you are not treating it well, but you cannot retrieve it. And it turns out that if you have no feedback at all, usually you get far too much dense gas. So it's like you need a bit of both. And the disadvantage of those boxes is that you do not have self-consistently this injection, but the advantage is that you can control it. So by moving back and forth, the hope is that you can build a solid picture, but this remains to be done.
Patrick, we have also a question from Zoom. No, it was an old question, so Marta says never mind. But Marta, use Slack to ask questions, okay?
All right. So that's the final sort of product. So that's the Schmidt chemical relations. The pink points are data. So the red things are when we have feedback only. The blue points actually are from a paper by Kim and Ostraker, which then probably are finding, from what we could conclude, similar trends than ours. Also, they may be also playing with the potential. So whether it's exactly the same thing, we discussed with them. It's not totally clear, but at least the points were fitting nicely with ours. So when we have sufficient driving, okay, then we can make it more compatible. And the reason why the situation, I think, is a bit more confused is that recently there was this paper by the SILT people in Garching, where they seem to find better agreement without driving. I would say probably a bit too high, so I suspect there is a trend of if they will continue, probably, I suspect, they will find the same disagreement, but I cannot confirm. In any case, both teams, they are not able to probe the full dynamics of this Schmidt chemical relation. So that's where we are at the moment. So we need to clarify this, and I hope this will be the case in the future. But for now, this is where we are. All right. So I'm switching now to the question of the
Was it?
Yeah, here.
Oh.
At the very end. Thank you. I was just wondering about the simulations, etc. Which are the initial conditions, specifically, for instance, for the chemical composition of the gas? Like, is predetermined as a standard composition that we find in nearby galaxies, or can we extrapolate, for instance, this kind of results to pristine gas that we are expected to be found at really high redshift galaxies, for instance?
So there have been a diversity of simulation. The simplest have no chemistry at all. So you have a cooling curves, which assume some typical galactic metallicities. And some have been using explicitly chemistry. I don't think for the star formation rate it will make a big difference. Maybe if you really go to a primordial gas, then of course temperature may be much higher and you may not get the two-phase medium and so on. So in this case, this could make a difference. I have no experience of that particularly myself. But I think even if you go to a metallicity of 0.1, maybe even 10 to the minus 2, I don't think it will make a big difference. I don't know exactly where the transition will occur, but 0.1 I think makes a difference.
Yeah, okay, thanks.
Right, so the second pillar that I was saying of the star formation theory is the stellar initial mass function. So that's a sketch of the initial mass function. So you have the peak there, and then there is this sort of like, I don't know, polar law or the high mass slope, and then there is this sharp decrease, which is the Broglie friction. And that's true data from various crystals. So there are several main features that are interesting. So first, a polar law regime usually sounds a bit like something which is scale-free, typically, to produce a broad range. And then we have a peak. So it sounds like a scale-free regime, and then something is setting a mass, a typical mass. So that's a possible explanation. I mean, this is my interpretation. So if this is correct, we have to understand what are the physical ingredients in this two regime. And then there is these questions which have been there for a while, the IMF was universal and so on. I think we are getting a bit away from that, because now there are something like established variations, or a consensus that there are some variation. Still, you may say it's like universal in the sense that there is a broad diversity of conditions, including in those clusters, and given those variations, you may have expected to have more variation in the IMF. So it's like it's relatively robust to the physical conditions. In the sense, we can say it's universal-like, or robust, or whatever you want to call it. All right. So, how to explain the slope of the IMF? So there are two types of ideas. I'm not going to go into detail because it will be any sort of thing you have to do. And so, the first type of ideas, which have been proposed, I guess, by Zidekers and Bonnell and Bates, is this sort of competitive equation business, which in my opinion is a bit similar to other ideas, stochastic equations that, for instance, Shantanu-Basu have been put forward. So the way I present it to myself is that it is stochastic in the sense that you cannot predict in those models what would be the final mass of the star before the process is over. Okay, so it's like competition. So you have a really random equations, and if you start with the same mass for everybody, you could say at the end of the day which would be the winner or the biggest guy. So it's more like a random equations of gas. And I'm just giving you here quickly some of the assumptions, if you want to dig in the paper and to go through. The important ideas is that they tend to produce for a spectrum with a slope that is actually close to the Salpeter exponent of 1.3, minus 1 in this case. On other assumptions, they will find maybe 1/2. Well, so it depends, but it's a poor law, not so far from Salpeter. The same for the stochastic equations. But of course, there are some discussion, there are some free parameters here that you can use. Right, so the second type of theory which has been proposed is more based on the so-called the first and checker type of analysis done in cosmology. The idea is that you have a density field which presents fluctuations, so density fluctuations all over the place, produced typically in our case by turbulence. So this linked to this very same idea of a density PDF, the same as the one we used for the star formation rate. And so the idea is that you have to do a scale-by-scale analysis. So it's like you have a kind of window function. Okay, like you smooth your density field at some scale. Okay? So that you produce, when you do your smoothing, something like big cells. Okay? And then you can, inside all cells, you can look at whether this particular density fluctuations is supported against gravity or not. And supported means that you have to look at all the supports. So you have thermal support, which at the very first level is isothermal, and then you have the turbulent support, and that particular gas is actually scale dependent. Okay, typically we say that it follows a Larsen relation or Kolmogorov relation, whatever you want. Yeah. So it's proportional to the radius, to the 1/2 or the 1/3 or in between, depending on your favorite model. Okay, so this gives, if you write the Weyl theorem, essentially, mass, an unstable mass, which is a function of radius. So in the normalized units, okay, this will be thermal support, this will be 1, and then you have the Mach number, which accounts for the turbulent dispersion. Right? Okay. And so then what you have to do is you have to sum over your fluctuations. So what you say is a bit like the same sum that for the star formation rate. This is your density PDF. This is your density. Delta is the log of the density. You have a threshold, but this time it is scale dependent threshold, given by this one essentially. And this mass, you essentially split it over your mass spectrum, because you say, well, the mass which is unstable at a scale R, okay, is at the end of the day producing all the stars which have a mass below the mass that you obtain there. Right? So it's an equality of mass, but you do it on a scale-by-scale analysis. So it means you have a continuous parameter, which is the scale. Okay? These sort of things you really need to dig into yourself. I'm just trying to give you in words the flavor of it. So you can then derivate this with respect to the scale, and so that will remove this integral, and you will get the mass spectrum. So that's the essence of it. And physically speaking, this picture is deterministic in a sense that you can more or less predict what will be the mass of the star from its reservoir, so before collapse occurs. Okay, so it's different from competitive accretions in the sense that just looking at the gas distribution, there is a blob, this is unstable, okay, so I can predict that this blob is going to give me a mass, a star with that mass, essentially. That's the idea. Okay? Those two ideas, they don't need necessarily to be in conflict with each other. Okay? Actually, I think they probably are both working in a different regime, and to some extent, and that's part of, I think, of the future work, to understand exactly what does what. But I don't see any reasons why some of those ideas would not be at play simultaneously. Okay, and that's typically the sort of predictions we can get from those models. So that's the type of gamma indices As you see, there is not a single answer because first it depends of your thermal support, it depends of your turbulent support, so which one dominates, and it depends whether your PDF is log normal, which is typically the PDF you get from pure turbulence, or it depends if your PDF is due to self-gravity directly. So what happens is that during the collapse, you develop typically an R-2 profile. An R-2 profile translates into a PDF, a density PDF, which is rho proportional to the -3/2, which means that you can, the idea is that you can produce during your collapse new objects which are triggered by the gravitational collapse itself, by the amplification of density due to gravity. So it's a sort of fragmentation. And so you see, you make actually interesting prediction. In particular, you see, you can make it very different from the classical salpeter IMF, gamma to the 0. And the first time when I saw this, I was saying, what the heck is this? But actually, I saw this in simulations. Okay, in simulations, in some conditions, it was completely flat. So it's okay. And so we come back to the equation and so on and find that, oh yes, if we assume this, that's what we should find. And then I realized that actually that the type of IMF that have been found in pop-free stars, which are exactly the conditions which corresponds to this with a very strong thermal support. Okay, so they have these cores which are very massive and very hot. So I suspect this is what is happening in those calculations. And then you can have, here you will find when it's turbulent support and the normal, you will find salpeter, which is a regime. And then you have this regime, which is probably a bit too shallow. So the picture is this one. So this would be your D and D again. So typically at very at large masses, the PDF is set by say turbulence. So you would expect salpeter. Then as you go deeper in the collapse, you become more shallow because you change PDF because you are now really in the collapsing regions. And then later even you start being dominated by the turbulent support, so you switch to something flat. Of course, and this is continuous. That's the underlying. All right. So what's simulation find? So I just pick up a series of simulation, and you see there is diversity of cases. So it's not easy to interpret those immediately. Broadly speaking, I think they would find something like a power law, but also you see some very big, flat regions sometimes. So part of the community effort now is to try to explore more systematically the various regime, and I would say to try to understand each time the physics which is behind. And for this, I think we need very much models, maybe not those ones, maybe those are just all wrong, that we need to be replaced by something else, fine, fair enough. But in any case, I think we really need not to rely exclusively on simulation, because they are such a mess that you can say whatever you want, you can move your hand and say there's a little bit of that and that. Okay. At the end of the day, what you want is a model that you may use as a grid to interpret your simulation and try to converge on the physics by confronting your simulations as much as possible with some reasonable model, reasonably simple model, without too many parameters to fit. And make predictions. Very important to make predictions. Yeah.
Can you say just in a few sentences? So are we looking at simulations that are similar in their setup and assumption, or are they wildly different and then they all result in the IMF?
Yeah. I would probably need, actually there will be a review coming out soon by myself and Mike Bronish, when with this being discussing all of that, in a very systematic way. It will take a lot of time to do that. I mean, typically, well, maybe I can. Okay.
Zeta coffee.
that has been used a lot is typically 1,000 solar mass clouds with various assumptions for the barotropic equation of state. I'm coming to this in a sec, and various assumptions for feedback and so on. I don't want to discuss all of that yet because it will come in too much detail. Let me discuss some more simpler case right now. So now I'm coming to the question of the peak. Okay. So those are two sets of simulations. Okay. So we take 1,000 solar mass clouds with some prescribed density and some prescribed velocity. There is no feedback at this stage. So this is purely isothermal, and this has a standard equation of state, meaning that we switch from isothermal to adiabatic in order to mimic the transition from, the point where the dust becomes opaque to its own radiation, right? And remember, there is this critical exponent, gamma equals. So what is striking here is that in the isothermal case, as you crank up the resolution, you see that the peak is actually shifting towards smaller and smaller mass. There is a peak, but it is shifting to smaller and smaller mass. So which means that in this case, the peak is artificial. And that's a danger of this type of calculations for structure in general. And actually, it's not only simulation, it's also observations. Whenever you look for a density distribution, you may be sure that you will find a peak, just because you have finite resolution. So whatever you do, there will be a peak. But then the meaning of this peak needs to be understood. And in this case, you have an example where it's completely dominated by euronumerics. Okay? If you do the same thing, but this time with this equation of state, you see, in this case, that the peak doesn't move. So it seems that here the peak is robust to resolution at least. So it's probably physical. Or at least it is not, if it's not physical, it's not due to resolution. Okay. So this I wanted to remind, I showed you already, and there is this switch between gamma and 1 for solution very important. So I just put this graph here to remember of this change of equational state, so the first collapse and the second collapse. And this part here, okay, has a gamma which is larger than 4/3, which for gravity is something very important. So the question is whether in your simulation you have included something like this or not. And actually, running a series of calculations, so again, 1,000 solar mass clouds, which is a compromise between statistics and numerical effort or the numerical method. You can actually vary the equation of states. So you can vary those parameters here, the density at which it becomes adiabatic and the exponent. Okay, so that will change essentially the properties of the first sample. Okay, and what you see is that if you look at the peak in all those calculations, and if you plot here the mass of the first sample, you see there is a correlation between the two. Okay, so this brings to the proposition that what sets the peak of the IMF is the mass of the first sample. That's the idea that you may get from the calculations. There is an important, of course, apparent caveat, which is that the mass of the first Larsen core is like 2 or 3 × 10⁻², and the peak of the IMF is 0.3, so 10 times larger. So it turns out that in the simulation we do see this correlation with this factor 10, and there has been some proposition from those paper and also Coman and Tessier, that this actually is due, this factor 10, to the tidal forces around your first Larsen core. It's not like a standard ISM place where you have a high density. You are sitting in a regions which is surrounding gravitational potential. And plus, you have an R-2 envelope around. So you have intense tidal forces there, which tend to shear apart your fluctuations. And so the idea is that the core gets like protected from nearby fragmentations. And so you tend to accrete all the mass which cannot fragment has to fall in, and this typically produces a factor 10-ish. That's the idea. The second idea actually is from Matthew Bate and Mark, is that the stellar feedback is helping to reduce the fragmentation. Okay, as you form the protostar, it starts radiating away, largely because of the accretion luminosity. Okay, and from that, you, in a sense, modify your local Bonner-Eberts mass because you heat the gas around, and this therefore may create a peak, a specific mass. And so, in Max book, for instance, there is this formula which is given, and which seems to be also very independent of the density. Okay, so simulations are going on there. Again, I would see that we need more time as a community to analyze carefully simulations with different theories, try to decipher what is in good agreement and what is not in good agreement. And that, I think, will take time. Okay, so that's my opinion. That's where we are at the moment. Okay. So as a very first result, okay, in those series of calculations from this paper, where we actually have a radiative transfer, not just the prescribed equation of state, but really radiative transfer. We change the efficiency of the accretion luminosity from 0 to 0.5. And so we do see some influence on the mass spectrum, which, for instance, here, when you have an intense accretion luminosity, becomes a bit broader. But we don't see really the peak shifting. Okay, so for the moment, I would say my interpretation is more in favor of, so the feedback is important, huh? I mean, don't get me wrong, it's really making a difference. My personal feeling is not for the peak, but this is only my personal feeling, so this needs to be confirmed. All right, I guess I finished for one sentence. So some preliminary preliminary conclusions. I would say this, of course, is diplomatic. Much progress been done. That's important questions. For the SFR, in my opinion, it's clear that there is a major role of the kinetic energy to regulate star formation. Okay, to me that is constant flow. Not magnetic, for instance. I don't believe it. Magnetic field will play a role, but not at the level of reducing by 2 orders of magnitude CH. Then where I think it's not clear, it's what exact role is playing the stellar feedback. And maybe even more advanced statement or questions. Is stellar feedback playing the exact role that turbulence would play if with some driving? Because of course it's a diverging motions, and very often it's really close to the star formation actions. Also maybe not that much from the supernova. So you see, I'm not completely clear, but that's part of the questions we need to understand. Sorry?
I thought that the stellar feedback drives turbulence.
That's exactly the that's exactly the point. Stellar feedback drives turbulence, but it's not only this, because at least for the jet and for the H2 region, it's less clear for supernova, because supernova, they come very late. They come after most of star form already. So I think supernova tends to create probably essentially turbulence in the ISM. But H2 regions and winds, they are very much where the stars are forming. So maybe here it's not exactly turbulence, maybe it's more like diverging motions. But that's part of the questions we need to better understand. And of course, do we have a contribution from the large-scale turbulence, like the one that is taking place at the scale of the galaxy and cascading down? I would certainly vote in favor of that, but we need to be doing more than vote. So this needs to be assessed. And regarding the IMF, I think there is a consensus that overload is due to a combination of gravity and turbulence. That's why we get this self-similar type of regime. Whether it's stochastic, like competitive accretion, or deterministic, I would probably say carefully that it's a bit of both. But whether it's 10 or 90 or 90 or 10, this may depend on the probability of the conditions, of the physical conditions. So also that's something that needs to be better assessed. The jets have been mentioned this morning. I think jets are important because they modify actually the initial conditions that otherwise would lead to something that would be too flat or a peak that would enter the right places. But again, it needs to be filtered. And then the question of the peak, which in my opinion, and I think the two main theories for the peak would share the same type of ideas anyway. It's a major deviation of the isothermal behavior. Okay, something like a adiabatic type of transition. Whether it is due to the dust opacity and whether the peak reflects the mass of the first Larsen core, or whether the peak reflects the feedback. Again, I think we need more work and probably careful estimate or careful comparison between models and simulations. And I think I'm there, so thank you very much.
Questions? Yes, great.
I am Matilde Fernandez from IAA. I wanted to ask you if you really believe that there is a peak for the IMF in the stellar regime. Do you think that it really peaks for reaching this 0.078 solar masses?
Well, this I think you should ask. I mean, myself, I never be engaging myself in sort of estimate from observation, so I tend to believe what my colleagues have been telling me. Sometimes maybe a few have not, but this year.
I'm making this question. So I pose this question because the stars that are to the left of the peak are more and more difficult to be detected. The brightness of the stars when you enter in the M stars, these are 60% of solar mass or below. They become more fainter and fainter, but not as it was before, but much faster. So I'm not sure. So I've been thinking about this for a while. It's not that the question came now, but so the stars are too faint, and even if you are in the solar neighborhood, you start to have problems to detect the most fainted. So the ones that are.
My question, that is probably a question for you actually, is that people, there is a great deal of discussions and careful analysis in trying to get complete surveys, but probably Nuria is more competent than me to answer this.
Then I speak with her, but
yeah, but she will speak just after.
Yes.
So maybe you will have the answer.
So I reformulate it, and I finish my question. Do you think that there is going to be a mass, an stellar mass, after which the formation of those stars is going to be, so the number of stars that we get are less than for others more massive? So it's the first question I said. Do you think that there is really a
Well, I mean, just from a simple analysis, if you assume salpeter all the way, and you have to have some final mass, because otherwise you get infinite total number of mass. So you must cut this somewhere. Okay, so whether this somewhere is 0.3 star mass, as I said, I'm not the most competent person, and probably Nuria is the best, more competent person in the room, but yeah, that's what there will be a cut somewhere, that's for sure, whether it's there, ask yourself.
Patrick, Nuria will answer with their talk and Marcus.
Well, I was going to comment on
go ahead.
this, right? So you're right that, this is very hard if you're looking in the field. You can't find brown dwarfs easily. It gets really hard. Which is why when people are trying to determine if there's a turnover in the brown dwarf regime, they tend to look at young clusters where the luminosity difference is much, much smaller because things are still hot from forming. And there are surveys, for example, of Orion, where they at least claim they are complete down to 0.01 solar masses. They found every single object in Orion down to 0.01 solar masses, and they report very clearly that they see a turnover. So you're right. I mean, it's hard to do in the field, but that's why people don't do it in the field.
Okay, you have 1 more minute to get chocolate and coffee, right? Do we have coffee now,
Yes,
right?
we have a coffee.
You can get chocolate and then get your coffee. Questions? Come on. Okay, another teacher has been there.
No chocolate. It's just a comment on your star formation rate. You had a question at the end there about large-scale turbulent driving. I didn't find anything that you said in the context of the star formation rate stuff particularly controversial. I mean, it seems to me that like an obvious that you'd have to have large-scale driving. It seems that the kiloparsec box is missing a really important component, which is the...
but it could be a detail, or it could be, I don't know, 10% of the feedback. So at the end of the day, it may not be fundamental. I mean, that's...
Okay, so is the controversy like how you try to implement that driving in order to kind of...
Yeah, I mean, before this paper came, before this paper came, I think there were 2 groups, so Evo Striker and us, we were pretty good agreements. Also, as I said, they may be varying the large-scale potential, so this may not be exactly the same thing, but I mean the point seems to agree remarkably well. And then they published this, which they have a star formation rate which seems to be below us, but there may be also a definition issue. So it's a complicated sense. I'm not. Yeah, we should try. I can say so. What I suspect is that if they would continue go to higher current density, I suspect, just from this slope, that they may have the problem as well. And so maybe they have a bit more feedback because they have cosmic ray sort of thing. So maybe they have different choice of parameter. I don't really know. And I mean the point is that we are far to go up to the the full Schmidt-Chemical relation, and we are missing more than 1 order of magnitude. So,
Okay, time for coffee. See you in half hour at 5:30.
Joe, it's good to see you. Good to see you. How was your trip?
Well, it's, I was thinking if you hadn't, I haven't seen it yet, you could do that, but otherwise I think I might just do it Friday afternoon.
How to change them?
Yeah, yeah. 3 episodes, yeah. Yeah.
Chemistry, organic chemistry. But there's also give dynamics. And I work with simulations and everything. But I never worked with astronomical background. So what do you have to include if you want to find out the magnet you don't need magnetic fields, no? For each one. Okay, okay.
So that's why I said no, the magnet is just
how to wake up depressed every morning like oh shit, I have to work.
yeah. I have to, but I'm studying. So as I said, like I'm just
But you're
so the previous one we did only just right and anybody we are only dealing with so we don't need that always kind of simple that one. But this time I was saying that's what I tried to do. Concerning the internal distribution is to do the insurance in order to introduce them we apply that. So I'm just starting working on that so I can come much.
The fluid dynamics is when I was teaching it, I thought it would be really difficult. It's quite interesting actually because it's because it has very simple things. I don't know, from statics to the dynamics, fluid has different behavior than solids. So and they are actually even flux. The fluid flux, it's actually really complicated, but it's just modes of the same stuff actually. It's just changing interactions a little bit of the matrix of the cell you're using, for example. This is actually the precision that you're doing. If you see a very big cell, like this is contribution, okay, you click up and
I think
you have physical sense. Actually, I didn't say it's really complicated, but how do you actually, constraint feedback, you really don't know. Just
equation or something. Yeah, sometimes you like you say, okay, just I say it doesn't make sense.
And you work, are you able to work on this? And because I'm an observational guy, so for me it's observational observations. I cannot just fake them. But theory it's completely different.
Yes, that's why, for example, when you work, you try to compare with the observation. For example, the one I did. So I work in one so these are like stars. China bound to 80 of the galaxy, right? So I mean, to identify them and like I use the simulation, so you have to separate them from the galaxies and try to identify where they those lists, right? So it's really difficult actually observations so then you use different techniques so that they know that you have to see, compare with that.
And how does they just
It's good, it depends on, for this one it's very different because they are in different ways. And we use the somehow compare
and how do you want to?
It's good.
So what I'm listening, you're already in the end of your PhD actually, so in the middle at least.
Yes, I'm in the middle.
Not in the
And
beginning.
this, I'm kind of finishing the working, the next one is the middle.
Okay.
So, the one I'm talking about business community.
They are close.
Yeah.
This seems like a very opening subject. Do you want a coffee? Because I will give a class in 1 hour, and maybe I have to go. So it's very far away? Or?
No, I think it's like 7
and a half.
I think it's 70 minutes walk from here.
Okay. I thought I would be able to taste on my No, I don't I is in.
Yeah.
Okay. Okay. Everyone already won. Ah, yeah, you will come here.
Вот я, собственно, летом был в Тайване, типа гитарщик, короче. И там они тоже постоянно посылали свои композиции, и там обычно постдоки, и очень летом,
Okay, today is really a walking day. Yesterday I worked in the night. I didn't find a restaurant. It was I gave 2 classes yesterday. It will be your future. You're a researcher now. As soon as you get there, you work as a teacher. Would you like to?
I'm actually a
Yeah. In the school?
So here is so after I finished the operation and so I just like to assist squares. So I just then after I got my master's, I did master's. So
симулятор называется.
Really, yeah, well, okay, so you have but still, 4 years and a half, master's degree, I don't know, I don't know if you did it, so you could...
So I finished my
You're the only one? Like, have friends, brothers and sisters?
I have one older sister.
So only women?
No, I have 2
Okay, you're the only one physics. Physics. They must be probably like saying, you should really start working, real work. It's not like this. My grandmother always like this. When you start working, this university stuff. This is a work, you know. Let's have a proper.
Yeah, sure.
Ну, без проблем. Ну, то есть,
Yeah, well,
так,
I'm running like
Нельзя.
in hotel. I suppose
Положить туда, и потом я тебе расшарил, собрался, я приезжал.
Ah, the class, you finished the class at 8.
Yes, it's from 6 to 8. So,
I think the dinner is at
terrible to
8:30.
I'm sorry.
Математика 2 часа, и мой мозг все, он больше не способен ничего.
Снимаю. Давай.
Я понимаю, что здесь лучше бы было 4 года. То есть сейчас там все происходило в режиме для университета, еще не было тем, как учиться, и было время как-то что-то делать. Хотя, по сути, английский уже к половине пищи везде. Надо статью выписывать. Здесь общались с теми, которые я второй год не значит, они какие-то славные, у них так все хорошо, они все. Это, наверное, себе. А что там вы научно выходите, бегаете куда?
Ну, пофиг вообще. Ну, типа, очевидно, он поддерживает время, как бы. Ну, это как? У нас, короче, очень тупая ситуация перепишет.
¿Dónde está sentado Rainer?
Detrás del abrigo negro.
¿Aquí?
Ahí.
¿Quieres que te lleve una galleta? ¿Estás bien? ¿Un
No,
café?
no, no, he tomado ya, gracias. He tomado, he tomado. Tú ya. No quiero más café.
He quitado cosas en la lista de
Lo he visto, lo he visto.
Y ya que me dijiste que te llegan todos los mensajes que te ha Emilio a Celia, pues claro, yo pensaba que iba yo sola y que te daba el ok. Pero si todo va a recibir notificaciones y eso...
Está aquí. Bueno, queda alguien más aquí.
No, yo.
A tú y yo, ¿no?
No, es que más que nada... y esto, pues, esto es para celebrar la Navidad.
¿Qué son estas cosas?
¿Qué?
Pero, ¿es uno de cada?
Sí, puede ser que las perlas LED sean un poco más. Es que...
¿Esto? No, esto.
pues, no sé cuántas personas van a venir, es para contar la gente.
Aquí vienen 100, ¿eh?
Solo.
Solo 100, claro.
Así, pues que añade un poco más.
Hola.
Bueno, ¿estás bien? Entonces no te traímos
Sí,
nada.
sí, no, gracias.
Io so io che tiene che controllare se ragazzoli che non moleste mucho persone.
¿Por qué dices eso? Yo soy buena gente. Compro panettones por mi equipo.
Vai, su. Ah, che viene? Ci scappa il 15.
Как ты боишься?
Ну, как бы да.
Я понимаю, что это... Из того, что я уехала, я как бы не увидела вот этого всего оттока. Я
Ну,
понимаю, что...
не, я помню, как год назад бегал сишь, стал воротом, теперь твоя позиция. Ну, ребят, ничего не стреляйте.
Я причем ничего и не делала, мне просто приходило 10 тысяч рублей.
Ну, хорошо.
Да я даже не против была бы что-то такое. Прикольно. Но мне кажется, она искала больше на Дашу, там Даша как-то очень мощно пыталась вериться. То есть это как она была очень принципиальна. Ну, то есть у меня тоже так. Я тоже не должна быть аффилирована по контракту ни с каким другим универом. Что мне тоже нельзя было. Но они никак не знали, что мне там никаких статей.
Ну, если хотя бы...
Если бы кто-то мне включил статью, но я бы сказала, что мне не надо включать эту статью.
А сама ты, наверное, не ставишь это.
Ну, типа, я не написала бы ничего. Хотя нет, мне как раз вышла статья. Вот меня научат заниматься по диплому. Потому что не стала. Вот. Потому что, ну, мне было не принципиально, подожди, я думаю, вот какой профессиональный покрасила, да? Прямо она вот резко сейчас все. Не, ну, на самом деле, я хотела
А смотришь на журналистов?
особенно. То есть вот мы статью добили в даже апелляции стали ставить.
Это хорошо, потому что у нас, допустим, с Гриничем очень длинная история. Вот помимо того, что у нас гранты хотели подрать, у нас всех людей, которые находятся в позиции, их отправили в достаточно. Потому что вы не можете закрыться без границы, там, если нет командировки, вот. И из-за этого, ну, как бы, народ не хочет себе ставить за эту апелляцию. Их нельзя получать, ничего нельзя получать, а при этом еще ничего сложного. Различно общались, что ребята очень нормально, там, нифига народу, который как бы много чего делает, но не хочет вообще никак с вами жить, потому что там всякое у нас нормы выполняются, вот, и, типа, у нас есть все еще ребята, которые хозяева, которые за границу тоже не хочет отпуска, но все равно ставят апелляцию, вот, и ничего, не небольшой коллег, вот, смотрю, ничего, нормально.
Нет, ну вообще, по-моему, сейчас
у вас народ уже увольняется. У нас народ сейчас, типа, чувак, третий курсник, нормально тут попал. Он типа вот сейчас подумал, что девочка рассмотрела, попал. Скорее их личная инициатива.
Вот, я такого не было, мне просто, мне нельзя сказать, что слишком не план, это не просто PhD поступили. Я должна 3 года заниматься чисто этим проектом. Ну, Анна оплачиваемая. Я по-моему пишу, в итоге не знаю, что это вообще такое, пока я не приехала.
То есть ты вообще как бы поменял, ты просто позицию делаешь?
Я просто увидела на выпустить позицию, не то, что как-то другой стал. Увидела, что, я не хотела писать, потому что он зарплату не скидывает, потому что зарплата почти намного больше, чем у обычных PhD. Я такая, почему другой? Ну, то есть она все равно низкая, примерно как уровень европейский, но не поступает. Интересно. То есть как бы
Ничего себе. Я недавно что-то больше берете злоты, перевожу в евро, получается 700 евро в месяц. Разу на это проверил, где все правильно. Я могу у нас гаишь вообще ничего не делать. Нет, типа, ну да.
Девочка с миллионером бегала.
Там прикольно, короче, то ли полунаучник, то ли научник, то ли знакомый. Я больше всего позиции Маратка, американская
Esto es como los aviones. Si puedes estar en casa de la emergencia, a mí siempre me dan instrucciones de cómo se abre, no sé qué tal, y luego me dicen que tengo que ayudar a evacuar. Pero, vale, ¿puedo ayudar a evacuar? No, estoy dando instrucciones. Ayuda. La verdad que... Esto es como cuando están en los Simpsons que hacen el simulacro de accidente nuclear con Homer. Y Homer sale corriendo, atranca la puerta y dice, el primero.
El vídeo de que se van a estampar y que los leones en la rama y el león se llama más movillo hace. Pero es que es un filtrado, toda la mañana que por la mañana, y eso es cuando le tocan una fiambrera de estas antiguas, sí, a los safaris todavía se lo pagan. Porque se ha comido galletas en mal estado. Para que no les demande. Pues eso, el mejor episodio es cuando Juan entra en el programa de sí, ya lo vamos a cuando le toque la mano, le pegue una patada en la espinilla, le pellizque la mano, que diga, señor Thompson, usted no es homenaje. Señor Thompson, pero tú de repente decides, eso es que tú estás en Brasil. No me iba a despertar. Sí, es el 97, como has visto, siempre yo veo algún capítulo después de es Nuria, me has dicho de astronomía y astrofísica.
Ah, sí, muy bien, se me ha olvidado.
Y a lo mejor me ponen las imágenes de portada.
Sí, oh God, esto sí que vale. ¿Sabes que no te digo?
Luego pensándolo con el teléfono.
Y esto es drama, serio drama, porque Paco nos dijo ayer que estamos
no lo sé. Esto parece
por la perspectiva futura. Bueno, eso luego se puede discutir con sí. Me dijo, ¿todavía se puede tener tu posición de puesto? Y yo bueno, porque Sandra se ha separado de mí por mi perspectiva.
Eres un cencerro de las historias. Estamos de chiste y ya cuando están nuevas la gente sabe que
claro, es que no, creo que no entiendo por qué no están juntos, pero bueno. Sí, durante la relación normalmente pasas menos tiempo que estos dos ahora. Está muy... Es que no tiene sentido. Justo ahora que se ha podido no, entonces no puede. Claro, yo estaba en una misma reacción. Claro. No entiendo muy bien, es que según él, porque como no ve ella, es muy duro. Claro, es que además es que
we are going to start soon. Very soon. I have a question for you. Do you check Slack? Can you lift up your hand if you check Slack? No, yeah, the Slack channel of this conference. I know everyone has Slack, but this channel, do you follow? I'm going to share a Jupyter notebook that you need it for tomorrow for the lecture I have. And I think I didn't plan to share it because I think it's very easy. But actually, if you want to already start to look in the Jupyter notebook and start to familiarize yourself, and also look out to randomly sample a uniform function, okay? Because you need to do that. I did for you one of it, so you need to do the next. Okay, so now, Rainer, do you have an announcement or anything to say?
No, but before I forget it, I wanted to say something. I mean, Patrick has done 3 lectures today. And he had the bad luck he had to do it on one day, and we have others also, like Nuria, for example, also because we have had some lecturers who couldn't come on short notice, so they jumped in. So thanks a lot. I mean, this is really. I mean, good thing is we have the conference, so, and the positive thing is, so we have the conference dinner tonight, so you can relax. We have tomorrow afternoon off, I hope you all know. And that's all. Conference dinner is at 8:30.
8:30, yes.
Okay. And we can probably walk together from here, and if not, I hope you all have checked the place. It's a hotel that is close to downtown, it's not far from here.
Okay, then we are ready to start, and we have Nuria talking about the initial mass function as inferred from observations. So, thank you.
Angela. Well, I would like to start by thanking Patrick because he did already an excellent introduction on the initial mass function from the theory side. So this makes my life way easier now to present my slides, which are going to be especially focused on observations and especially focused on the low mass end of the observations. So this was not planned, but also thank you for the question that you asked us before. I will try to answer you through my presentation now, but if you feel that at the end this is not answered or you want to add anything, I will like very much to hear your opinion. Okay, so I will start my presentation on the initial mass function, and needless to say and define what is the initial mass function, I will just show this cartoon because I like it very much and I show it every time I have the opportunity to do so. So essentially this is a schematic view of the mass function. So here we have stars ordered from very high mass stars, sun, and going to the low mass regime, brown dwarfs and planets. And essentially when we measure the mass function, we are trying to answer which is the proportion between high and low mass stars. So which is the most common output of objects in our universe. And well, the mass function is really important for many different processes. Already, the mass is an intrinsic parameter of stars, not like brightness that changes through the life of a star. The mass is intrinsic and is conserved for most of its life. It only can vary at the end when the stars die and explode as supernova or planetary nebula. At this point, they lose part of their mass, or in very interacting binary systems where there might be mass transfer from one of the components to the other. So these are really specific cases where the mass of an object would not be conserved, but in the majority of cases we can take mass as an intrinsic parameter. Then also the initial mass function predicts the number of stars in clusters, the galaxy, and the universe. So it's also an important parameter for people who are doing simulations. And it's also an important parameter to compare our observations and the results of simulations. So I have structured my talk in 2 main blocks. First, I will make a review on the observational challenges that we have when we try to determine the mass function. So maybe this will be obvious in some cases. I hope it's not too trivial, but I think it's important to review these sort of limitations in a lecture like today. And the second part maybe is going to be more interesting when I will show the results of mass functions in some of the nearby clusters. So, first of all, if we have to study the mass function, where would you start investigating? I've heard that we have plenty of more chocolate for today.
Yes.
So, so I think it's an easy question, but maybe someone wants to answer. Where will you start investigating the mass function? Yeah.
We want to look at like open clusters in the Milky Way.
Open clusters, that's one possibility, yes.
Or globular clusters.
Or globular cluster, okay. Star clusters in general, that's a fair approach.
Can we say that in like,
Yeah, please use the mic, everyone, because the online people cannot hear what you're saying. Online participants.
You can choose, okay?
Okay, where else can we measure the mass function?
Or Angela, or you could repeat what persons
Yeah,
are
I
saying.
can do that.
Thank you.
And I can
Please.
send it out.
Where else can we measure the mass function?
Molecular clouds?
But would you measure the mass function or the core mass function? Like the initial mass function or the core mass function?
Chocolate or Spanish? And more there?
Yeah, I think.
Please go. I can run through the room. I've been sitting all day.
Star formation region where there's a lot of young stars.
Yes, but so star forming region, I would still consider it as clusters, associations, star forming regions. Yeah.
Are you interested in a massive star or not? Because you could.
In the field of field stars?
Okay, very good. So taking a sample of our galaxy. Good, and there is a third place. It's a bit different. Anyone wants to go, I guess, the last one? Yes?
maybe dwarf galaxies.
In external galaxies, indeed. So these are the three main key systems that I would think that one can one can measure the initial mass function. And each of these systems has its own pros and cons, advantages and limitations. And it's interesting to measure them in these different places and then have the chance to compare. So for instance, in clusters, we have the great advantage that all of the stars are coeval, so they are all the same age, so we are measuring exactly the output of our star formation board, which is exactly the definition of the initial mass function, right? And on the contrary, if we consider a group of few stars, here we will have different populations mixed, mainly old stars that may have gone through stellar evolution, etc. So we will have to correct the mass function in the field in order to eventually get to the mass function. Then, if we decide to go for clusters, I already started discussing it yesterday, but depending on the clustering algorithm that we have, the census and biases of our selection, this will maybe also be important when studying the mass function. And finally, extragalactic, so I will really not comment on this. I think this will come more later in this week. But here the advantage is that we can investigate very different environments and really test what Patrick was saying, whether the mass function is really universal or not. But here the main difficulty, I would say, is that it's very hard to resolve individual star counts. And so we also have to make some assumptions of how to go from the brightness of these extragalactic observations into individual star counts. So for today, we will be focusing on these two, and I think this will come at the end of the week. Okay, so this is also a slide from yesterday where I was already pointing to the importance of knowing the completeness of our catalogs. And if we are going to use Gaia, Then there is this effort from this Gaia Unlimited team who are trying to produce the selection function of Gaia. But this is only the starting point, as I was saying yesterday, because if we later apply some quality cuts, and what's even more important, if we have our own techniques and our own algorithms to identify subsamples in this catalog, this can have biases and can have different completeness and recovery rates at different magnitudes, and this is important, and this is very important to take it into account when determining the mass function. Then, if we want to go beyond Gaia, because in the end Gaia is limited to magnitude G20, 21, and we are even interested in the low mass n, and we want to also investigate the mass function in very young systems which are still embedded in the parent cloud. We need to go to deeper surveys and also surveys which occur in the infrared. And then this can become quite messy when you have have to combine the photometry of different surveys. So here you have an example of the patchy footprint of this survey in the Pleiades cluster. And also, you may end up having different magnitude limit and spatial coverage for different magnitudes. And this is an important thing to take into account, and this is related to the completeness of your final sample. So, more on the completeness, this is what I was saying. So it's not only about the catalog, but it's very important of measuring the completeness and contamination rate of the clustering algorithms that we have. So now we have, as I was mentioning yesterday, we have many different groups which are publishing lists of open clusters, and this is fantastic, but I think it's equally important, especially for studies of the mass function, to publish the completeness and contamination of these catalogs, because otherwise the mass functions that we will determine from them could be biased, especially because typically when you go to painted objects, you start losing stars, and then it's very hard to know whether the slope you are measuring is the actual mass function or is the sensitivity of your instrument or your algorithm. This is regarding magnitude, but this also is regarding spatial distribution. So I was showing some studies that are focused on the centers of the cluster, while if we start opening these search boxes, we find many clusters, many stars, farther away from the cluster center, and if our cluster is mass segregated and we only look into the center, again, the mass function is going to be biased to the stars that sit into the center. Okay, so now I would like to say also a few words on how to determine how to select a sample from the field to obtain the mass function. And it is important to obtain volume-limited samples and not magnitude-limited samples. Our observational catalogs are always magnitude limit because in the end our instrument, our CCD, is limited to the brightness, but this is not the, but since we have massive stars which are way more bright, way brighter than low mass objects, we will see them at larger volumes than fainter stars. So this is going to introduce a very known bias. This is the Malmakis bias. And essentially this bias, what is producing is, so if we were to compute the mean magnitude of all these stars, the mean magnitude or luminosity would be something around here, right? But if now we not select a volume limited but a magnitude limited, so the faintest and farthest away stars, we are not going to observe them, and the mean magnitude that we will observe is brighter than the real one. And this is important to take into account or to correct if our survey is magnitude limited. Then, okay, so I tell you have to make volume limited, but in the end, measuring distances is complicated, and even Gaia doesn't measure directly the distance. What we measure is the parallax. And there is this very interesting article from Xavi Luri where they discuss the importance of taking into account, of determining essentially Bayesian distances, because here the idea is that if you try to invert directly the parallax to obtain the distance, when the star is far away and your uncertainty is large, the distribution of distances has a long tail, and essentially, so if you cut only in distance, you will be selecting this thick line. So you will, so for instance, let's say that you want all the stars that are closer than 5 kiloparsecs, you would be selecting all these stars, but you are going to miss all these, which in fact, because they have a large uncertainty, when you try to invert the parallax into the distance, you have this long tail that you should take into account. Okay, so this is all the initial part on these selection problems, but let's say that we are happy with our selection, either if we went with our volume limited sample in the field, or you have your favorite cluster that you made a perfect clustering algorithm and you are very happy with it. So then you can obtain directly from your list the magnitude distribution. Magnitude and brightness is something very easy to observe, and you have it for all the stars. So you can essentially count how many stars at each magnitude bin you have. And this is the magnitude distribution that, as I was saying, is a direct product of observations. So that's good. But magnitude and brightness changes through the stellar evolution. In particular, for young stars in the pre-main sequence, the magnitude of stars changes very rapidly. They cool down rapidly. So it's not a very useful parameter to compare the magnitude distribution in different regions, because if they are at different evolutionary stages, the result is not going to be very useful. And what really we want is the mass function. But masses are not a direct observable. Masses are not a direct observable. In fact, they are best measured in binary systems, but this is only possible in few cases. When we have all the information of the orbit, we can resolve well the binary system, and we have information of the complete orbit. Then, using the Kepler's law, one can obtain the mass of the system, but this is not in the majority of cases. So what we do in practice is we use these stellar evolutionary models, which are great because they allow us to obtain masses in a very simple manner. You just take an isochrone and place your star in this diagram and look which is the mass that corresponds to this luminosity and temperature. But to do so, you need to know the age of your star or your cluster. And this is important for high mass stars, but this is crucial for low mass stars. Because for high mass stars, you see that in this pre-main sequence, so this is essentially, I should start here. So you're seeing the color magnitude diagram where I have overplotted the models at 1 million years and 10 million years. And because we don't have uniform models for high and mass stars, for high mass stars I'm plotting the parsec models, and for low mass stars I'm using these back 15 models. And essentially what you see is that for high mass stars there is a difference, but for low mass stars these models really overlap one on top of the other. So if you don't know which is the age of your star, and you have a star here, so it's very easily to confuse the mass of the star. So is it 0.01 so solar mass or is less than this. So you see, and this is really important, and this is an important source of uncertainty, which can be easily of the order of 30% of the mass. Okay, then let's say that we know the age of our clusters and we can obtain individual masses for our stars. Then what we can obtain is the system mass function. But this is not going to be yet our mass function, because what happens here is that if we are observing a star that is in fact a binary star, but it's not resolved, we will see something that is brighter than the actual two stars. So when we look into the mass function, this is not a nice mass function. This is just a schema to discuss my point, right? But let's say that this is the system mass function that you observe, and if you correct it for this effect, then you see that in fact these high mass stars will decrease because some of these will be resolved into pairs, and on the contrary, you will have a few more low mass stars. But to make this correction, it's very important to know the binary fraction of your system, and this also probably depends on the mass. So very high mass stars are more often in multiple systems than low mass stars. But I think probably Ignacio is going to discuss all this just after me. So just so you know that this is also another observational difficulty in order to obtain the mass function. And finally, also the mass function is not something static, but also something that evolves with time. So let's say again that this is our schematic mass function to our mock mass function to play with. And if we let this mass function evolve, essentially what we see is that on one side, the most massive stars are soon going to explode as supernovae, and we are going to miss them. And at the low mass end, also they might be ejected or dissipated from the cluster. So the shape of our mass function is going to keep changing with time. So then it's very important either to measure it in very young systems when we still have similar conditions to how these stars were formed, or we need a recipe to correct for stellar evolution and dynamical evolution. Okay, so far was the boring introduction on the observational biases. Now I will try to show some results on different mass functions that have observed, mainly in low mass clusters, but also a bit underfield. Okay. So I will start with this first result of Salpeter. So this is the first article that introduced the mass function, and it's very interesting to see how the slope of this mass function that he measured in 1955, it's still correct nowadays. I think this is really interesting. So this was really nice, but this mass function has a problem. Now it has already been discussed in the previous lecture, but essentially what we see here is that what does it happen if we continue to go to lower and lower mass objects? So in principle, purely this description of the mass function would diverge at very small masses. And in fact, in principle, this is not what we are observing. On the contrary, we see that there is a point where this mass function seems to find a peak, or at least a moment where this stabilizes and does not continue growing. However, this is what we observe, and also, so currently there are different ways of presenting the formalism of how to describe this mass function, but because this has already been described by Patrick very well. I'm not getting into details here. Essentially, I think an important characteristic of the mass function is the mass at which this peaks, and there are different formalisms that in the end can reproduce similar shapes, either a segmented power law, like this one here at the top, or something which is a log normal description plus a power law for higher mass stars. Okay, so, and what do we see nowadays using these surveys that I was mentioning at the beginning towards the infrared, focusing in very nearby star-forming regions where the objects are going to be close, so we can see faint objects, and especially looking into the infrared, so looking into the wavelength where these low mass and substellar mass objects shine the most. So this is a figure from a review from Stellar Offner in 2014, where she compiled the mass functions in different regions in the solar neighborhood. And so there are several features, I think, to discuss in this figure. So first, the good news is that we are able to measure this mass function in very different regions. And I would say within the errors here, it's hard to say whether these functions agree or not. Especially because many of these studies, I would say, they didn't make a big effort in trying to propagate all these uncertainties that I was mentioning previously. So all the completeness and contamination rates plus the uncertainties on the masses, this is really important to include this in here, and instead many people only report these Poissonian error bars that not necessarily are including all these sources of uncertainty. But still, I think what we are seeing is that there is this peak in most of the cases, but also the other problem is that very few studies reach into the end of the round dwarf regime and into the planetary regime masses. And this is essentially because you need very, very big surveys to get into this. And I will try to show a couple of examples where this was possible. One is in the Pleiades, and this was combining all these surveys that I was mentioning at the beginning. So here it was really complicated to get a proper selection function for the census that we had, but still looking at the complete magnitude distribution of the catalog, one can see more or less until which magnitude in principle the survey should be complete. And in principle, what these authors found in the Pleiades is that they were complete down to 0.03 solar masses. So what we are seeing here is that there is really the peak of for high mass stars, the mass function was similar to Salpeter's law. Here this is a bit steeper, but this is only because they need still to account for the white dwarfs that exploded already in the Pleiades. So in principle, if you account for these massive stars that have exploded, this would increase a bit here. And the other feature that we see is this peak at 0.2, 0.3 solar masses, similar to other regions. But we do see also this decrease in principle. And I think the very interesting feature of this mass function is that at some point we also see that this decrease stops, or there seems to be a plateau inside the brown dwarf regime. And now I will show another case where this was the topic of my PhD thesis, where I essentially tried to do exactly the same job in the region of Upper Scorpius and Ophiuchus, this one that you are seeing now in this image. And what we try to do is map all this region with, again, in this case, 74,000 images using different instruments in the optical, in the infrared. We also took the images, like old images, together with images that were very recent, and this large time span is very important to measure the proper motions and to be able to select the stars that are coeval and members of the cluster. So, yeah, doing this exercise of computing proper motions for all these stars in this region and selecting the ones which are co-moving and also the ones which align in this color magnitude diagram, we were able to find 3,500 members in this region, among which around 100 are planetary mass objects. So this was important because this is the first study that has significantly populated the mass function in the planetary mass regime. So as I said in the first part of the talk, so once you have your census and you are happy with your census, then the easy thing to do is to obtain the magnitude distribution. And this in principle only depends on the completeness and contamination of your catalog. This has nothing to do yet with uncertainties in the evolutionary models. So plotting this magnitude distribution, again, we could see that there seems to be indeed a peak in the mass function, and this decreases when you go to brown dwarf regime. And in this case, what we found really interesting is this feature at planetary mass objects, which seems to be statistically significant with the uncertainties that we have. And the completeness limit that we estimated is probably around here. So we are not yet sure whether this decrease, so this decrease could easily be the result of the completeness of our survey. So maybe this continues to increase, this we cannot be sure.
What was the threshold for the mass, the planetary mass?
So we detect objects down to, so, okay, give me one moment and I reply you. Because, so the problem is, when you ask me the mass, so which is the age that you take for this region. So we are considering this full region where there is Ophiuchus that one can argue that this is probably very young, of between 3 and 5 million years, but also we have many sources in this region of Upper Scorpius, which is likely older, between 5 and 10 million years. So the difference between taking an age of 10 million years and 3 million years is a big difference in the mass of these objects. And this is an uncertainty that we have and we inherit in the mass function. So essentially what we did to obtain this mass function is, let's imagine that all the stars are in Ophiuchus. We know that this is very optimistic and it's probably not realistic, but it's an extreme case. And this would be this mass function here. And also let's be very pessimistic and let's imagine that all these objects are in Upper Scorpius, so they have around 10 million years. So this would be the opposite case. We know that the solution is probably going to be something in between, and I think this is the mass function we obtain at 5 million years. So this uncertainty here, as I was saying, is inherited from the uncertainty in the models and the uncertainty in the ages. But to answer your question, so I think the lightest objects that we obtain are around 4 Jupiter masses.
That's great. That's incredible. I never heard about this. Well, I heard about the Mirde Hoy publication lately, but well, I really have my doubts. I'm from planetary exoplanetary science, so I really have my doubts on this, I confess. But anyway, it's a really interesting result. So I wanted to, for Jupiter mass is incredible. How could you actually get into that mass range? Just a question about the planetary formation scenarios for these planets. Okay, sorry. So do you assume that a typical time scale for this planetary formation? For the planet formation in this kind of scenarios, before this, you stated the age of the region. So this, if you thought about this, the time that it takes to form a planet, if it's acceptable that these guys are already there. Have you did you do your feedback against others that detect planets and see and check if this information is correct, or it seems logical, legitimate, these planets you found? For Jupiter mass. I don't know if I'm asking, I'm too clear about my question. So have you tested the bona fide, so the suggestion that we are sampling, have a good sample of these planets, or just have a few? Because, I really think that we found in late statistics that we have more or less one-to-one relationship in a galaxy like the Milky Way of planets and stars. So this is the last statistics. So this seems very strange that this keeps going down. So that's why I was asking, if you think, what's your comment on this? If you think this is a good result, or I think it's suspicious, I must say. I would say I would expect the increase again towards, for example, Jupiter mass planets, and then go to super Earth, planets. So if you can comment on this, sorry. I don't know if you.
So here.
You should expect a peak. Actually, I don't believe in this. And it's going down of the
okay,
planets.
well, if you let me, I will reply. So here, so far, I didn't discuss any formation mechanism. I plan to quickly address this in the following slide, but here only what we are showing is the results of, so we have this catalog where we search for objects that are co-moving and also follow along the same isochrone, and this is directly what we get. And what I just discussed a moment ago is that indeed we see that this is falling, but maybe I think this is the limit of our, the completeness of our survey, so this could easily also increase again, and here we are at planetary masses, so this planetary masses more or less begin. So this is for the magnitude distribution, that is direct an output of our clustering survey.
Okay.
Then, if you go to the mass function, so this is why I was discussing all the uncertainties, and you see that here the error bars are quite larger compared to here. Yeah. So here we see this decrease, but this is a mixture of the end of the completeness of our survey. So in fact, this was also, this is probably a lower limit of the true number of this sort of objects that we have, because, so first, we are quite confident about the ones that are here, because they have the same motions as the rest of the stars, they follow along the same isochrone, and some of them have also been confirmed with spectroscopy. So we believe that the contamination that we have in this mass function is really low. But at the same time, it's true that our survey has a limit, and we are probably going to miss the most embedded guys, objects which have a high infrared excess. These are very complicated to identify with our technique. So yeah, I'm not saying that there could begin, but what I'm saying is that this is going to begin increase again, probably here, but not here.
Okay, thank you. Yes, I also believe that we should expect another peak over there in the planetary mass. Okay, perfect.
So yeah, I think that's settled now, because I mean the problem is and this is amazing work, and this is free floating planets. I mean,
incredible.
This is free floating planets.
Incredible. Yes,
so I mean, of course, there's going to be lots more planets. I mean, you'd have to look at with interferometry each and every one of these targets, and then count planets again. But yeah. It's
a very exciting result. That's why I wanted just to comment, because I would expect a peak an expected peak, but it's not the theory. This is observations.
Yeah, but I think, so the point here is that we don't have less planets than this, but we probably have more.
Much more. Okay, okay.
This is the way I understand these results. I don't know if there is.
I had a very quick one, sorry, since it's about this. In the previous slides, you showed the spatial distribution. And no, the one after, yes. These are the planets.
Yeah, these are the planets. The red ones are the planets.
So, do you know there is a fraction of them that seems to coincide specifically with filaments? That
Yes.
filaments. So, do you have uncertainties for the extinction? Because the extinction is bringing down objects.
Yes, so those here are probably not planets but brown dwarfs, probably because they.
So those are counted when you do the mass.
But this is why we give a range between 70 and 170. So because these, I agree that these probably are not so good, but then the majority are in here where the extinction is rather low.
Okay, thanks. Let's continue. Unless other people have questions. No, go ahead.
Okay. Okay, so then that was the result in this region, but I also wanted to show for completeness a recent result of the mass function in the field. This was obtained for the Gaia collaboration team. This is not directly a mass function, but an absolute magnitude distribution. And essentially what I find super interesting in this plot is that they also see this feature here. But again, so this is already at the limits of the Gaia capabilities, so we don't know if this could easily also be growing again. And this was also to say that there are also some efforts in the very solar vicinity from the spectroscopic surveys, which are coming up with similar fractions of free-floating planets. So, very briefly going to the formation of this mechanism, so there are different scenarios by which these ground dwarf and free-floating planets could form. So one of them is that they could form in planetary systems similar to our own planetary system, and then due to dynamical interactions with other planets, or if another star comes very close to this system, so one of the objects can become gravitationally unstable and be ejected of the system, and that guy will eventually become one of these free-floating planets. Then they could also, in principle, form similar to low-mass stars, and here maybe Patrick knows a bit better what are the possibilities or limitations of this scenario for such low-mass objects. I don't know if you want to comment something.
No, I mean, the huge issue here, I would say, is the thermodynamics. I mean, I'm not speaking against those models in particular, but I think when we enter in the brown dwarf regime, and even before that, what kind of physics exactly this can be debated, but what is for sure, I think, is that we are not in an isothermal regime, and that's, to me, really what is missing in this model. We need to have a high resolution and good descriptions, and at the moment that's a challenge.
Okay. So, in principle, this, then also one could think either in a scenario where several cores are accreting material from the same gas reservoir. Sometimes if one of these objects is ejected before it accretes sufficient mass to become a star, it could also become a substellar object. Or also in the vicinity of hot massive stars, the stellar winds of these objects can also evaporate the outer layers of an accreting core, and this will become one of these brown dwarf or free-floating planets. So maybe some of these theories still need to be confirmed, but I think currently also the question is also which is the dominant mechanism, And I would even add which is the dominant mechanism at a certain mass regime, because it's also possible that for high mass brown dwarf this is going to be one, and for low mass free floating planets it's going to be a different one. And to finish this presentation, so I would like to put a bit in context. So we did some efforts to compare the mass function in this region of upper Scorpius and Apicus that I was showing. This is the mass function in red, this is the one we have discussed. And here we have overplotted a couple of IMF from numerical simulations. And so what we can see is that they more or less agree well until the half of the brown dwarf regime. This is true that here these models are at the limits of their resolution, so I'm not sure the comparison is 100% fair, but okay, if we take what we have, so comparing the fraction that we have observed in this free-floating planet, which we know that is going to be only a lower limit but a true fraction, but fine, comparing this fraction with what the models report, so we see that some of these objects could still form by this core collapse formation, while we also made the effort of comparing the fraction of free-floating planets that we observed with exoplanetary surveys. So here essentially what we are comparing is this fraction measured from the mass function to the fraction of exoplanets, so of stars which host a massive giant exoplanet, times the probability that this system becomes unstable, and this is related to the eccentricity distribution of exoplanets and the probability that one of these objects is eventually ejected from the system, and this comes from some simulations. So essentially here, I think the take-home message is that we are comparing this fraction with exoplanetary surveys, and also indeed it seems that some of these objects could be formed by this other mechanism. So I think we are not yet in the position of answering which is the dominant mechanism, but probably at least these two and maybe even others have a significant role at these substellar objects, and I think we need still more work, both from the observational side in trying to constrain better this fraction, trying to measure this mass function in other regions, trying to also detect all these objects that are still embedded, and also we need probably some answers from people doing simulations. So hopefully this will keep advancing in the coming years. And with this, I finish my talk, and I'm happy to discuss anything related.
Thank you very much. No more questions.
Now, I don't know if it makes sense, I was just curious. When you show the IMF for the Pleiades,
yeah,
there was like a piece of like incompleteness where it's like a solar mass. I was wondering why.
That's a very good question. So this paper is from 2015. So this is pre-Gaia. So essentially here we were comparing, I think it was TICO 2 data with ground-based observations, and this is the limit of the I think it was the TICO 2 catalog, and with the ground-based observations we essentially saturate the bright stars. So there was this small gap in which none of the surveys was complete. But with Gaia this would be easily solved because essentially it covers the whole world.
I have have to admit that this is the first time I hear about free floating planets, so that's really amazing to hear about that. And I'm just wondering if it's possible to get the velocity and the direction of motions for those free floating planets so that you can know like the origin of it.
So what we have is the proper motions. We have the proper motions thanks to the fact that we combine these photometric observations separated by 20 million years. So you can actually...
years.
Longest survey ever done. But by 20 years, so essentially you see how during these 20 years the star has moved its position. So we could measure the proper motions, but to measure the parallax and the radial velocity, I think it's not possible at the time.
Other questions? But I have a question. So this planet has been formed and then is ejected. How long does it take to form a Jupiter? A 3 times solar mass Jupiter? I mean, this you are saying it's just in time scale of 5 million years for this cluster, right?
So I think this is a great question. I'm not the right person to answer, but I'm not even sure that there is a consensus or whether this is even established. On the contrary, my understanding is that the fact that we are seeing all these free-floating planets ejected already at this stage, and probably we need this mechanism to explain the large fraction of objects that we have. So this is also putting a constraint into the timescale in which these planets form. But I am not really the person to answer regarding that.
I'm not the person to answer this either, but as far as I know, if you look at the protoplanetary distant clusters, they are gone after 2 or 3 million years. So it's very short, the formation time, lifetime. The formation time, it's a few million years at most.
I will come to you. Patrick, and then...
I had a comment on this as well.
Yeah. Shall I go?
I just got a small question, very naive. How do you know they're ejected and they're not just formed in small cores?
Okay, maybe I'll let him add.
I just had a comment on the time scale of formation. So the 2 main theories of giant planet formation, core accretion, disk instability, will give you different time scales. Let's say the longest one, the core accretion scenario, gives you a time scale of more than 1 million years for the formation of a Jupiter-like planet, plus or minus. And the other one, disk instability, gives you a shorter time scale. It could be even smaller, 10 to the 5. So 1 million years is really the upper limit.
And Amy, to answer your question, I think we don't know. So I think so.
Also, how do you know they're free floating? They're in the middle of the star forming region. Don't people estimate the space densities of free floating planets like out there in the middle of nowhere in the galaxy?
Okay, I think we are reaching the point of, again, it's a definition strategy. So what is a free floating planet? For me and for
something in a super dense solar region.
No. So it's way more easier than this. So whenever I was referring to free-floating planets, I was referring to objects that are lighter than 13 times the mass of Jupiter. So objects that are, and this is using the deuterium burning limit. So objects that have less than this mass threshold, I refer to them as free-floating planets. Now, there is people who argue that this is not a good definition because the deuterium burning limit does not have an important impact on the life of these objects.
No, but they're reasonably, by your estimates, reasonably low mass, so you're calling them planetary mass objects,
exactly.
right?
Yeah, that's
but
the
my
idea.
question, the thing I'm picking at, which maybe is totally unreasonable, is how do we know they're free floating? How do we know they're ejected? You know what I mean? Like,
so
they're in a star forming region.
Yeah, but we don't see that. So this is something that we said. We don't see that they are in. They have a star very nearby that we can't think that they are orbiting to. So, in principle, they are isolated. Not isolated. They are part of this star formation, but they are not close to a star, which make us think that they are orbiting this star. So they are free floating in the sense that they are like
they don't have an identifiable stellar mass companion or whatever.
But we don't know, in fact, if they were ejected or not. This is something that we are trying to find out about today.
maybe just I think from theory side, having an isolated core leading to such small objects is very challenging because you need to have an enormous density. And so that's, I mean, how do you get to such huge density in a completely isolated system? That's the challenge. I mean, fragmentation in a sense helps you because then you get the functional well of bigger objects, and so you take advantage of that to generate the fluctuations and the differences. So, I mean, if I should vote, I would certainly vote for some ejection mechanisms because I cannot imagine something else.
I'm just curious, can you explain a little bit more on the process of turbulent fragmentation? Because for you, I know that turbulence closes the collapse, so let's do the length scales of turbulence that causes somehow the frequency masses become really tiny. Can you just talk a little bit more?
I can, but
I mean, if you have, say, only turbulence, then you generate something like a log normal distribution, so you have a lot of fluctuations which are created by shocks all over the place, and that may be the seed, individual sort of fluctuations of further star formation. The issue is that turbulence only will not make extremely dense fluctuations because essentially you will not create density fluctuations much denser, I mean many fluctuations denser than the Mach number V2 times the mean density. So typically you will be limited. If you now rely on the gravo-turbulent picture, you mixed gravity and turbulence, which are extremely difficult to decipher. You have a mixture of those same fluctuations due to turbulence, but also to collapse. And so you get a sort of density PDF, which has a power low tail. So you have much more dense fluctuations that you would have without the gravity, but still you have seeds. It's not a pure like spherical collapse. It's a type of spherical collapse on top of which you have fluctuations, but then those fluctuations can be extremely dense. That's the essence of the gravo-turbulent collapse. I'm not sure I've been completely clear, but that's the idea. You combine the two in a sense, and thanks to this, you get extremely high density fluctuation. What limits you at the end of the day, as I was trying to describe, is when you start hitting the gas either because it becomes adiabatic or because you have feedback, probably both. So that will limit, in a sense, your ability to collapse and fragment. Okay. And then you can have further complications. Sorry, you can imagine that during the second collapse, which brings you up to the photostar, you could possibly create there even more fragmentation. This has been proposed, I think, by Bate in the 90s and something. I'm not sure there has been much effort in that direction, but in principle this is possible because the effective gamma is around 1 again. So if you again are in a phase of gravo-turbulence fragmentation in the second collapse, you could go even smaller and maybe produce those objects. This is something that is possible. Whether this really happens, this I would say has to be further investigated.
Okay, so for the power of chair, I declare this session. No, I'm joking. There's one more talk, but I need that you stand up and take 2 minutes, go around and come back because I see people sleeping or tired like brain off. I don't see brain activities when I look at you. So stand up 2 minutes, come back, and in the meanwhile, our final speaker of the day will sit down. Speaker, tutor, teacher, lecturer.
Really nice talk. It was really nice. I have questions, but later.
Los parámetros están separados totalmente. No, o sea, esto todo mal, o sea, pero es que funciona, es esto, creamos con respecto a una función de lo querido y ya está. O sea, era para probar si algo por 10 seguramente luego, no sé, sí, de todo mejorado un poco más.
Ten en cuenta también la variación de precios.
Sí, ya, hay que meterlo, pero lo tengo que meter toda la respuesta. Lo completo
Sobre sí que te da falta sobre todo para este tipo de o sea, es lo mejor. Porque guiarte del fotofita, que es la estimación de la que queda.
Bueno, en eso está bien. En eso está bien calculado, porque si es un prototipo con las líneas no está mal. Esta era la idea. Vale, aquí he pintado dos cubos, pero voy a hacer, lo tengo en cuenta de dimensiones.
Everyone, please come in. Break is over. We start. Please keep your name tag for the dinner. I think I don't know the name of more than 5 students right now. So when you ask the question also, say your name. By the end of the week, I promise to remember your names. But use also name tags for dinner tonight, otherwise it becomes a bit difficult to interact. And for the last lecture of today, we have Ignacio Neguerela, I hope it's correct, Ignacio, sorry, who will talk about stellar multiplicity, so right on the topic of multiplicity. Go ahead.
Okay, yeah, I'm Ignacio Neguerela from the University of Alicante, which is pretty close to here if you consider where other lecturers have come from. I know that I'm standing here between you and your free dinner, but you need to pay attention because everything, well, most of what you've been told is a lie. But it's not exactly a lie, to be fair, it's a thought experiment with very little practical application, because you've been told how to make a star, how to make a set of individual stars, how to measure the mass of a star, but there's no such thing as a star. Stars are in binaries. Okay, maybe red dwarfs like to be alone, it's normal, they are pretty miserable things, but real stars like to have company. And in fact, the more mass a star has, the more company it likes to have. So, binary stars. Probably the most famous binary star is this one, and I don't even know how it's called. But most stars are binaries. So most of the stars in the sky are binaries. Things that look like that. Just gonna give you a few examples of binaries. Spica. You've seen this star probably is like 10th brightest, 12th brightest star in the sky. If you wake up early tomorrow, you're gonna see it. It's the brightest star in Virgo, and it's the star that marks the beginning of the spring. So it's known by all the cultures in the northern hemisphere. And in fact, it's a binary consisting of a B1 giant and a B2 main sequence star in a 5-day orbit. So you can see that it is a binary. You need to have spectra to see the spectra of the two stars moving around. And then it's a double-lined spectroscopic binary. It's double-lined because there are two stars showing in the spectrum. So, bright star. I mean, even Sirius, which is the brightest star, is a binary, but there's a single-line spectroscopic binary because you only see the main component, because the second component is a white wolf. So it's difficult to see it in the spectrum. Okay, this is the star closest to us. Of course, I mean, we have the sun, which is single. Next star has to be a multiple system, because that's what the statistics are telling you. Here you have, this is Alpha Centauri. This is a triple system, and this is what we are calling a hierarchical triple system. Why do we call it hierarchical? Because it's organized. You have a binary here, and you have the other star out here that sees this binary as a star. So it's a binary containing two things, one of which is another binary. This is the only way in which a dynamical system can be stable. If they are not hierarchical, they will be dissolved very quickly, or they will merge, or they will destroy themselves in some other funny way. So, in fact, this is the star closest to us, this one here, Proxima, and it was until recently it was suspected to be part of the system, but recently it was confirmed with ESO data that it is moving. The orbit is absolutely huge. No one has seen a significant part of this orbit. But there are many things to learn here. Just by looking for images, I learned that there's a congress on this star. So there may be many things to say about it. It's in Nice. It was in Nice this year, so you missed it. Okay. And this is the orbit since per year. These are thousands of years. So it's going to take a while before it goes around the other star. Of course, we know that this is a triple system because it's the closest one to us. I mean, this is at 1 parsec. If it was any further away, we wouldn't see this, and we'd think that this is a binary. And the central binary has a star which is pretty much like the sun. It's a bit more massive and a bit older, I think. There's a slightly less massive star. These are the two central binary, and then there's this red dwarf that is Proxima that is going out. Okay, this is what I call a binary. This is an object that we were studying a few years ago, one of my PhD students. And this is a double-lined binary, which also happens to be eclipsing. And as Nuria told us, if that thing happens to be eclipsing and double-lined, then you can learn everything. Everything. You can use Kepler's laws to know the masses, you can use geometry to know the sizes, and if you happen to know the distance, you can even do magic with stellar models, see how the temperature is distributed. You can do everything. You know? And you can see here how we have parameters for everything in this system, from the orbital period to the level of oblateness of the stars. And they are oblate because they are in a 1.1, 1.2 day orbit, and they have masses of 38 and 32 solar masses, so they are going around like mad. It's a system which is synchronized. They go around their own poles as fast as they go around each other, so they move at about 350 kilometers per second. And this is a very good candidate to merge before the two stars die. And people think this is the one way in which we can populate the very upper part of the IMF. By merging two stars that are formed normally, you generate a very, very big star. Have a question?
Yes, I'm sorry, I'm not an observer, so I was wondering, how can you measure that the star rotates around its own axis? How can you measure that the star rotates around its own axis, because rotating around each other?
You can do that with the shape of the lines.
Okay.
The lines are deformed by the rotation, and we have models that allow us to assign to a given size a rotational velocity for the stars.
Are they stripping?
Yeah?
Are they stripping each other?
Probably not. Probably not. They're probably on their way to form a common envelope. Even more interesting things happen. This star, probably heard about it, Ithakar. One of my colleagues who sadly passed away many years ago used to say that this was the most pathological star in the sky, because there were people who had dedicated their whole careers to trying to understand this thing. Ithakar is a star in the Carina constellation. It was pretty bright until 1842, when it suddenly decided it wanted to be brighter, became as bright as Sirius, and then disappeared from view. And when we had telescopes, we went back and looked at it, and we saw this. What's that? Ejector. Something's been ejected from where the star is, which is here. And how has this happened? People wonder for a long time. With HST data, they were able to see that there was a second star in a 5.5 year orbit, a very elliptical orbit, and so they speculated that maybe the second star had somehow somehow dragged the star and forced this ejection. Nowadays, people have learned a few more things, and we have a much more complicated scenario for this, which is basically this. We had a triple system with two very massive stars and another star in a hierarchical triple, just like Alpha Centauri. The most massive star, that was something like 100, 150 solar masses, died young, started passing mass to the companion, and because of the way in which angular momentum is behaving here, the system widened. So this was the strip star. This is really a strip star, a very massive one. And this was the companion, having received maybe 70 solar masses from the other one. And then the C component found this guy moving out, and through some sort of a weird billiards in the sky, they swapped places, and the two stars in the middle now merge, and the merger produced the explosion and the ejection. And the star that is orbiting now is the remnant of the originally more massive star. That's what people think that happened. And as you can see, there are lots of interesting things that happen with binaries. And you can have much more complex systems. This is Castor. This is another bright star that you can just go out and see it. It's the two stars in Gemini, Castor and Pollux, and this is sextuple system. It has been known to be binary for a long time. Its period is about a few hundred years, and we've been observing this since the 18th century, so we have an idea of what's the period of this system here, A and B. And recently it was found to have another thing in a large orbit, which is C. And when you look at them, each one of those two is a spectroscopic binary as well. So A is an SB1, B is an SB2. So basically we have A is an hot, relatively hot A1 star of about 2.5 solar masses with a something companion, which cannot be seen. The B is a similar star with an M2 companion, and C, which is in the long orbit, is two red dwarfs, which are forming their own binary. And again, you see the hierarchical system. Each one of these systems behaves as it is a single star from the point of view of the other components of the binary. So as you see, there are many interesting things that can happen with the stars in systems. And if you want to know how frequent this is the recent review paper by Stella Afner, which is most up to date on binary statistics. And here you have plotted two things, which is the number of multiple systems, which is here, which is number of binaries minus number of triples, minus number of quadruples, plus number of whatever plus, divided by total number of systems. And this is this line here. And then this is the fraction of complex systems, which is more than 2, divided by total number of systems. And this is this line here. Okay? And you can see, as I was saying, boring stuff here, 25%, not 0. Sunlight, 50%. Up here, everyone. Everyone is here. Not just here. Everyone is here. Every massive star you look at is 3 or 4. Okay? So this is a good approximation to the distribution of binary fractions. This is a slightly different plot, which is the number of companions, which is if it's a binary, it's just 1. If it's a triple, it's 2. If it's a quadruple, it's 3, divided by total number of systems. And this is slightly more complex line. And you see, typical O star has 2.2 companions. Yep.
Are these, where are these multiplicity determined?
I'm going to that. Okay. So, I highly recommend that you have a look at this paper, which is where most of these numbers come from. It's Mo and Stefano. I'm not recommending that you read it because it's really boring, and recommending that you have a look at it because it's basically an endless discussion of how you measure this and how many biases and incompleteness, problems and assumptions go into getting these numbers. Okay, it's extremely difficult to get these numbers because you are comparing very different things. Just to give you an example, this is where the statistics comes from for solar type stars. Solar type stars, they refer to this paper. This paper used Hipparcos data to create this volume limited sample. Just remember what Nuria said. You cannot go for a luminosity limited sample. You need a volume limited sample. So you select here a few hundred solar-like stars with distances from from Hipparchus, and you do the statistics, and you go and check every possible way in which an object can be a binary. Do we see two stars? Do we see two stars when we look with a real spatial resolution? Do we see a spectroscopic binary? Do we see a double-line spectroscopic binary? And you add, and you get to this number. A volume limited sample out to 25 parsecs. And this is the distribution of orbital periods in logarithm of days. So you see most of these binaries have orbital periods of the order of 10,000. It's a few years. And this is the size of the orbit in astronomical units, which is something that people who do low mass class like. We measure things in solar radii, which is a more interesting number when you are trying to compare how big the orbit is compared to the star. But it's easy to go from astronomical units to solar radii. It's a factor of 200. And well, so you see most of these binaries are extremely wide. Stars are like that, just going around very slowly around each other. Now, of course, I mean, this is very well done, and it's complete out to 25 parsecs. So, you, for example, want to know, when we go to the old stars, and I'm saying that they have this multiplicity, how we compare like with like. Can anyone tell me how many O-type stars we have out to 25 parsecs? Anyone?
O-type stars.
O-type stars.
Students, not teachers.
Zero?
Exactly 0. Yeah. You remember Nuria was showing yesterday how we can go out from the sun looking at different associations, and you go to 100 parsecs and you have a lot of associations. Do you know how many O-type stars there are out to 100 parsecs?
0.
0. Yeah. If you go to the Vera region that she showed, I think there are 2 there, at around 120 to 130. And then you go to the Scorpius Centaurus, and there isn't any, even though maybe Antares was an O-type star when it was young. It's about around there. Beta and Delta Scorpii are just B0. So then you need to go to Orion, and there are a few there. And you go to the Orion Nebula cluster, and there's an O6 star. Okay, and you already have. You're 400 parsecs away. You have, well, you can count with the 2 hands. Okay, so you're not comparing the same. Can anyone think of another way in which you're not comparing the same? When you compare solar-type stars with O-type stars?
Students, come on, give a guess.
Who wants a chocolate?
I'm ready.
Yes?
Go ahead.
The range of ages.
Yeah?
Ages.
Ages. If the sun is a typical sun-like star, it is a 4.5 billion year old star. And these things, if they are O-type stars, they're less than 10 million years old. So you are not comparing things that formed at the same time. And another interesting thing is Nuria mentioned yesterday that the oddity that we are in the middle of a cavity, but there's an even bigger oddity which I don't quite understand. If you look around us, young stars have solar metallicity. And we tend to think that this is natural. But the sun is an old star that came from somewhere inside the galaxy. And the fact that stars that are forming just now around it have the same metallicity, to me is beyond understanding. It's a big coincidence. But again, if you go to M-type stars, I think the sample is complete out to 10 parsecs, and most of them are very old objects. So there are many biases that come into this determination. So we have to find the binaries using different methods. This is a spectroscopic binaries where you see the two stars. You see there's a star here. You see the shape of the lines. These two stars are almost the same mass. One is rotating fast. One is rotating slowly. And you can see as things change how the two move with respect to each other. This is Sigma Orion. It's another star that is there in the Orion complex. There's a third component in a 160-year orbit that we don't see here because it's rotating very fast and it's diluted somewhere here. And you can use this to measure masses. But Kepler's third law, if you think about it, you have here M is the total mass of the system. So for a given orbital period, you have very different separations depending on the mass you are having here. I mean, two solar mass stars, two massive stars are 50. Therefore, you have a factor of m to the 2/3 there, which goes from 50 to 2. So it's a big number. And so the detectability of a star with a given method depends on how big the orbit is, how far away it is. You can find stars that are separated by a given distance nearby, like Proxima Centauri, which you can see with the naked eye if you have a photographic plate. But if you go to the Large Magellanic Cloud, you're not going to detect stars that are separated by that amount. So many different biases. Also, the velocity, you need the two velocities to be different. This is for a circular orbit, but it's essentially the same for an elliptical orbit. Total mass divided by separation, square root. So if you have a lot of mass, it's much easier to discover a binary. And if you have astrometric binaries in which you just see them wobbling around the sky, you have different effects. And of course, we haven't got many of these because this is extremely difficult from the ground. But we are expecting Gaia to give us a lot of these systems in the next data release. And this is extremely good because this is going to cover a range of separations that we are not currently sampling. This is a question.
Sure. It's just a very good question. Why is it not that the early releases of Gaia, like DR3, they didn't provide the astrometric binary? Did they need a longer time?
Yeah, they basically need a longer time period to be sure. I mean, now what they are doing is marking them as not very good solutions for single stars, but then they're going to go back and look at the ones that are probably binaries.
Thank you.
Yeah, there are a few that have been published and people have been doing searches for black holes around nearby stars and things like that. But yeah, most of the data is still not published. So this is from a talk by Rodolfo Barba a few years ago, in which we look at the multiplicity of O-type stars, and here you can see the different methods that are used. This is all the survey he was conducting. I will briefly mention it now. These are spectroscopic detections, and these are cases in which you see the two stars. Okay? And you see peak here and a peak here. Is this real? No, obviously. It doesn't make any sense for this to be here. Why is this? Because here you are getting two separations of about 1 year, so the velocities of the stars are not big enough to separate them as spectroscopic binaries, but they are too close for any method that we have to separate them, because these things are O-type stars. They are all more than 1 kiloparsec away. So these sort of separations, you can go back to the to Kepler's third law and calculate the separations. These is typically something like 100 milliseconds or something like that. We have no way of seeing that, even though people are now using the instrumentation on the VLT. X and his team are using the instrumentation, sphere, and things like that to look for these sort of things.
Do we understand those uncertainties? Oh, do you want me to? I'll wait till.
I should have questions if people don't like it, but
Thank you, Mitchell.
very few.
So do we understand the biases in these methods well enough, and maybe with a little bit of theory, to kind of estimate what the filled-in version should be? Like, should it be Gaussian? Should it be flat?
If you ask Maxwell Moe, he will say he understands it perfectly. It's very well described in his paper, but I don't know, really. So, there's also how we build these things. And I want to show, this is the work we've been doing for, well, we have essentially finished now. We've been doing it for 15 years. This is Western 1, which is the most massive cluster in the Milky Way. And basically what we were doing is collecting spectra of individual stars for basically over a period of 6 years, using the DLT with the French giraffe and multi-object spectrograph to observe relatively bright stars, mostly supergiants. Supergiants are very bright, so they are normally SV1s. Here you have two examples. You measure the radial velocity of every spectrum, you run a period searching algorithm, you find something, you see if it makes sense, then you try to fit an orbit. These are orbital fits for two of these systems. It has a companion in a 16-day orbit and with an eccentricity of about 0.01, essentially 0, which is normal because if you have a supergiant, it's extended, and there are tidal forces that circularize the orbit. And here you have something which is in an 11.1 day orbit with an eccentricity of 0.4, so this one hasn't been circularized. And so doing this and looking at an enormous number of systems over quite a few years, you build solutions, and then you build something like this, in which you have all the systems that you have, and essentially you have the ones with these ones which circles around. There are orbits that we have solved. These ones within this white rectangle, they have data that even we are sure they are binaries, even though we haven't got enough points to build the orbit. And then everything here is difficult to say because the stars have pulsations, and this introduces radial velocity variations, and we don't really know if they're pulsating or they have a companion or whatever. And those here are probably single, even though there's a small chance that it is a projection effect. If the orbit, you're not seeing it like that, but you're seeing it the other way around, you don't see any radial velocity variation. So you can correct for this because inclination is easy to guess what the bias is, unless there's a reason why stars in a cluster are aligned with their orbits, which I think current models of star formation don't go that way, but who knows. And so you build a cumulative distribution of systems with orbital period, and can say that the fraction of binaries in this star cluster has a strict lower limit of 51%. And then you can do your numbers and say, okay, this is compatible with the other number, which is 100% here. But of course, this takes a very long time. It's very difficult, and things happen. And I was mentioning this. This is Rodolfo Barba, who was doing the OWN survey. and he had been collecting the spectra of stars. By the time he published this paper, he had 7,000 spectra of 300 stars, and he was basically doing every single O star visible from the south. He was doing it with a large number of telescopes. Problem is that one day he had a stroke and died. And 2 years ago, and of course there are more people involved, and many of us were collaborating with him. But of course, he was the person running the survey. He knew how things work. He had preliminary solutions that allowed you to know, okay, if I want to see what is the maximum velocity for this orbit, I have to observe it at this point. And all of that is probably lost now. It's a bit of a pity. But it happens, it's how astronomy works, and probably nowadays too many, I mean, even large collaborations are basically a one-person effort. Because the way astronomy works is you have to lead or you are a failure. And no one can work for another astronomer, and when you apply for jobs, they are going to evaluate you on your leadership. So big collaborations are a bit of a problem. There's another way of doing this, and this is the method that Yves Sanin and his collaborators in Amsterdam have developed. And this was done to measure the multiplicity fraction in the Tarantula Nebula in the LMC, where basically you have a few observations of a number of objects, and then you measure the highest difference between the two spectra which show highest difference in velocity, and you plot it here as a distribution. Then you go and you do a lot of Monte Carlo simulations of millions and millions of binaries in different orientations, ran all sorts of Bayesian statistical tests, and from those you decide what is the multiplicity fraction after applying a number of corrections that they discuss at length. Of course, this is a much faster way of doing things, and this is where this number of 100% comes from. But I'm sure they've done a very good job. But I don't like the idea of having to go through a model to get an observation of it. Anyway, this is from the Maxwell Mode paper. You have all sort of systems here with all sort of, because you need a couple of hours to understand this figure, so go and look at it. Different methods, different types of binaries, what you get from each one of these combinations is interesting. So these are the numbers of binaries, how we get them. You can see it's not easy, sometimes it's just a number, but it takes a while to get them. And what we know is that this is from the very beginning. Stars are made like this. Yeah.
What about the mass ratio?
The mass ratio is more difficult, you know. I mean, if you do it the way that the Amsterdam people are doing it, you get a statistical mass ratios. For massive stars, it seems to be pretty flat. But for less massive stars, it's difficult to say. But again, from the review by Stelaufner, you see here statistics. These are the statistics of different main sequence stars. These are the statistics for pre-main sequence stars. And you can see, again, these are the different regions that Nuria has discussed, and someone else has discussed, I think, this morning. And you can see the binary fractions that you can see, using different methods as well. This is for class 0 objects, I don't know where. And all these are low mass stars, you can see. And this is pretty similar to this. So the distribution of binaries among pre-main sequence stars is pretty similar. Of course, around pre-main sequence stars is much more difficult to do this. Spectroscopic binaries are difficult because pre-main sequence stars are hidden. They have disks that produce emission lines. So I'm not very sure how they do it, but well, they have managed to produce these numbers. Things that are profoundly embedded, you can only get statistics for visual binaries if there's another star close to it and measure the distance there. There's a lot of interest in this field. This is a recent paper by John Tobin. You can see they are conducting a survey of stars in Orion with instruments that give you extremely high spatial resolution, ALMA and the VLR, to see if these objects are really single or not. And you can see that they're finding lots of things that look like binaries. They have statistical tools to understand if they can be random objects projected, and then they calculate the masses to see if they are likely to be bound. And from that, they are getting a large fraction of multiple systems among the stars that are forming in Orion. And one thing that is pretty, let's say, comforting is that the multiple systems tend to be brighter when you consider the light from all the stars than the single stars. And this is what you expect if you are probing the same population, different characteristics. They've done it in two regions, the Perseus star-forming region, which is relatively low mass, and here they lack statistics to be sure, but here in Orion, which is bigger, they're getting this as a statistically solid result. And then you can see here the same plots as before, multiplicity fraction, companion fraction for the different classes of objects that were introduced on Monday. Class 0, deeply embedded, class 1, ones with flat spectra, and to get to there. Okay? And you can see these are all low mass stars, and you can see the multiplicity fractions are 25–30%, which are the same ones that you get in the field. So it seems to be something that comes from the formation, and something that the formation models have to reproduce. How do you produce binaries? There are a number of mechanisms that have been proposed. There is this instability, in which you basically have a primary that is being formed, and the disk has a density which is a mass that is high enough to create another seed that stops accreting as well, and you directly form the two of them. You have a filament that is fragmented with two cores that are very close together, and the gravitational attraction moves them to be together. And then you have dynamical interactions in the clusters that are being formed. If you have a sufficiently high density of the stars, these things are likely to happen. And you can have, for example, two things that have formed like this, which are very different in mass, collide, and they play their billiards there, and you end up with a hierarchical triple and star doubles. These are the mechanisms for producing binaries. And this is again the same from the review, but here with a simulation showing this case and an observation that they believe reproduces the simulation. So core fragmentation, a single core produces 2 stars. Filament fragmentation produces 2 cores that then get together. Disk fragmentation, dynamical evolution. These are the simulations, and these are the observations. And well, similar. So, there's if you're interested for examples, there's this recent review by Edgar Frost that was there was a workshop on binaries in clusters at ESO in September, and I was there, and the different presentations are on Zenodo. So if you go here, you can have a look at the review by Abigail, and there are many examples of these things happening in different star-forming regions, or what they believe are these things happening. There are different physical mechanisms that can produce or not these things. Of course, you have other lectures you can ask about these things, because I'm not the person. This is essentially a comparison of the size of disks measured somehow in different star-forming regions, for non-binary, binaries with wide orbits and binaries with small orbits, and in some regions, especially in the low mass regions, low mass star-forming regions, they were finding that objects with a distant companion had bigger disks than the non-binary and the binaries with the not so distant companions. And this makes sense because, okay, if you have a close companion, you cannot grow the disk. And if you have a distant companion, it sort of contains the disk and can allow you to form a big disk. But it seems that the most recent observations of places like Orion do not support this view. In Taurus, there was it's the other way around, so it's not certain that this really works. So there's probably a dependence with environment. You can think that if you have a wide companion and if you're in a very dense region, you're going to have another star going by and stealing your companion and just throwing it away, populating the free floating planets wide from worlds that Maria was saying. And there's maybe as well some dependence on the metallicity of the cloud. This has been claimed for low mass stars, but I don't think there's enough data to be sure that this works. In fact, there's a recent result by Furio who shows that the distribution of binaries in the Orion star-forming region is supposedly identical to that in the field, which would show that in a dense environment you form the same sort of binaries as in normal environments. Because we assume, which is an assumption, that most of the field around the sun, which is what we can see, is populated by low mass star-forming regions like the Taurus and similar things, while in dense environments you could expect other things happening. Perhaps Orion is not really what we call a dense environment. In fact, on Thursday we will see where we can find a bit denser environments, but unfortunately we are not going to be able to see what low mass stars are doing there. So that's the problem, that Orion is is our only test field, and you can call it a massive cluster in a sense. It's in the same sense that a mouse is a mammal, and it's a big animal because it's not a mite. But it's not gonna tell you what a lion or an elephant are like. So Orion is not a low mass STARFORM region, but it's not what we call a massive cluster. And this is a very recent paper by Odier, in which they show multiplicity frequency for giant stars for different spatial scales. You have here the separation probe by different methods in astronomical units, from here, which is about 1, up to 10⁵, which is very far away. These are the classical the STARFORM regions that people observe, and these are well, here you have Orion, you have M17, which is a more massive cluster, but it's further away, it's 1.5 kiloparsecs. You have Trampler 14, which is a pretty massive cluster, which is at about 2 kiloparsecs, and of course it's much more difficult to see low mass stars there. You have the Herdic AAD stars, which, as Mark mentioned, are the high mass equivalents to the T-Tauri stars. So these are stars that have completed their formation but still surrounded by this, and they typically have masses of 2 to 3, 4 solar masses. And I mean, you can do this here, but it's probably impossible to do this because they are full of emission lines of everything, and you cannot do spectroscopic techniques on anything like that. So you can see these are relatively massive stars, and you can see the multiplicity fractions are extremely high. Here you are dominated by low mass stars, and again you are getting the same sort of numbers as we were getting from the main sequence stars, between 25 and 50%, depending on mass. Interesting thing that came the other day, they go to N17, that, as I said, is a very young open cluster, which a number of O-type stars. It's not Orion, is something a bit more serious. It has about 15, and it may have a mass of 3,000–4,000 solar masses. And they find there are absolutely no short period binaries among the O-type stars. And as I have shown you, in the main sequence stars, there are many short period binaries among the O-type stars. So these people, these are again the Amsterdam and Leuven people who are now dominating the massive star field. They're claiming that if you look at the clusters, you basically see that as they become older, the radial velocities of the stars show a higher dispersion, and they think that this is due to the fact that binaries start being white, and so you see very low radial velocity variations, and then become closer and closer and closer, and so velocities go up. And
this is in a cluster environment?
This is in a cluster environment, yeah. These are all clusters.
So just repeating Higgs' law, but in clusters instead of in the field?
Yeah, well, these are numbers. You see that the universe are big, huge. These are all clusters that are typically at 2 kiloparsecs. So, I mean, you can see if an O-star is a spectroscopic binary at that distance very easily. And this is based only on massive stars. I don't know if it's true. These are mechanisms for hardening, as I call it, a binary. When it is still embedded, because there's a sort of friction with the gas, it can get in. But an O-type star that you see, I don't think is embedded in gas. So the only other mechanism that can harden a binary is to have a star triple system, and you need to change orbital angular momentum from the inner binary to the outer binary. So this is the interpretation of the facts, but worked by the same group, and this connects to what Nuria was explaining yesterday, has shown that there are a lot of stars being ejected from the cluster. And this is, they can use this to get a kinetic age for the cluster, but this is different from what Nuria was saying, because it's not the cluster dispersion. These are things that have gone through binary interactions in the center of the cluster and have been ejected at high speed. And so you can look at them and take the trajectories back to the center and see how long they've taken to get there. So with this method, they claim that M17 is 700,000 years old, starting, I don't know where when you put the zero, as Nuria was saying, is when these things were close to the center. Now, how do you eject these things? If all the binaries are very wide, I have absolutely no idea. You need a lot of energy to give them speed, and
what's the mass of this thing and velocity dispersion? I mean, you have the internal cluster dynamics also, right? I mean,
yeah, but this is the
and you will have encounters between them.
Yeah, these are the velocity dispersions, and it's down here. No, 7 maybe, and then these things have been ejected with velocities between 40 and 70, 90 kilometers per second, and are moving away from the cluster. I think the only way you can do this is through interactions between hard binaries. But at the same time, they are saying that there are no hard binaries in this cluster. So I don't know how this can happen. And this is from the same paper. You can have a look at this later. Basically, it's embedded massive chunks in stellar objects. All stars close to the sun, which is basically looking at the younger clusters in that diagram. And this is the field. Of course, the very massive stellar objects, we don't know their masses. We assume they are relatively massive because they are luminous. And just to finish, because Nuria has already done most of this, of course, the presence of binaries changes your initial mass function. This is quite obvious because you have that. For normal stars, luminosity goes like mass to a number, which is 4 or 3, depending on where you are on the mass. And if you have 2 stars and you think they are 1, they're going to be twice as luminous. But if you want to convert that into mass, you're going to take this. You're going to take this root to the 4th or something like that. So you're going to count them as a not much more massive star. But according to Pavel Krupa, this has very little effect on our knowledge of the upper main sequence, but it has a side effect, as Nuria was mentioning, down here, where stars are not that luminous. So possibly. And this is what I was going to tell you. If you have any questions, or if you just want to run for the dinner, but I think I deserve a chocolate.
You get 2 actually.
Thank you very much.
Yeah. So, question from 2 teachers, no students. Bad.
Hopefully,
Quick is dying.
Yeah, hopefully I'm just opening the floodgates for the students. So, given that O and B stars are basically 100% binary fractions, and close to high fractions for triples as well, one of the figures you showed in terms of period fraction for different masses of stars, I think it was one of the ones from Stella Offner's review. It looked like for O-type stars, not only are all of them in binaries, a pretty significant fraction of them are close enough to interact as well. So could you comment perhaps on how interactions are going to change the rotation, they're going to change stellar lifetimes, they're going to change the atmosphere properties? Do you think we're getting all of our assumptions about feedback wrong because we're starting from an assumption of here's what a single O or B star does?
Well, this paper by Kuksana, which is the one in Fame and Prosperity, claims that 70% of massive stars will interact with a companion during the main sequence. This has a lot of implications for many things. And just to give you an example, they claim that when you are estimating the feedback from the number of ionizing photons, I mean, if you want ionizing photons, you need very hot stars. So you are assuming that only things like 07 or earlier are going to be O-type stars. Now, if you have 70% of stars interacting with a binary companion, the most likely interaction is that they're going to pass them out of mass. And if they pass them out of mass, basically they pass the whole envelope. And what you get is an exposed core, which is what some people are calling the strip stars. And an exposed core is essentially a helium core at a huge temperature, which is emitting ionizing photons like mad. So these people claim, and there have been a number of papers by the group by Selman Link, that populations of the people who are doing populations in galaxy are underestimating by a big factor the number of ionizing photons you get, because these strip stars are going to throw a lot of really hot photons because they are very hot, basically. Yeah, so it's worth looking at it. That said, they had a number of predictions about how these things should look. And they have a recent paper claiming detections of quite a few of them in the LMC. But we haven't seen any in the Milky Way for some strange reason.
On this point, I was a bit confused by the Eta Carina scenario of the triple binary system, because do we see this stripped core?
No.
I mean, Eta Carina is very close. Shouldn't we see it?
Precisely, that's the point. Because it's very hot, it's emitting mostly in the ultraviolet, and it's very difficult to see it because the ultraviolet photons are eaten up by these huge amount of material that you have up there. It's like 10 solar masses of dust. So that's one of the reasons why people have proposed these scenarios, because we don't see the companion. We just see the envelope wobbling. We don't see the big star because inside the envelope, and we don't see the companion. So that's why this scenario has been proposed.
Okay. And Nuria, a question.
Okay. So my question was more towards this last result that you were showing at the end, this kinematics of these stars. So is there any chance to see the kinematics of the low mass stars in this region? Because, so the question is also, so could it be that the whole region is expanding? How do they know that this comes from the ejection of binaries and not a global?
Because they are too fast.
It's too fast.
It's too
very
fast
rapid.
for expansion. They are moving at 50, 70 kilometers per second from
Okay,
center.
okay.
Yeah.
Just quickly on Natakar, I got a little bit confused because I read a paper not too long ago, a few years, about little cloci, and if the scenario that you were proposing was related to that. Was it the same explanation, or is it
completely different.
Allí está el metro. O sea, yo no podré ir porque voy a acostar a los niños, pero va a
I
caer.
think most people
Y está el
think
metro.
that there was a merger.
Al metro es quien se tiene que identificar los
What
vegetarianos y decir,
merger?
yo soy vegetariano.
Maybe
Vale,
the,
perfecto. O sea,
the
normalmente
first scenario I
me será un nombre, pero es que hay 17 vegetarianos.
Ellos están
and
informados
the
de
other
los que son
orbital
Los
vegetarianos.
tienen el dictado.
sucks away the orbital momentum from the orbital angular momentum from the inner binary and force it into merge. Or this is a more complex scenario that
Nosotros solamente me lo ha dicho.
So the next one
También les
is
voy a
that
decir
the
que no
star
pueden
is
cambiar
very
de
hot.
opinión ahora.
No,
Siempre pasa.
Siempre pasa. Carmen lleva el dictado de todas maneras.
I mean, these are
Sí,
perfect.
Sí, sí, está bien perfecto. Como yo ahora soy quien ha puesto el bebé, porque le hemos quitado el pecho.
¿Sabes qué tal?
Sí.
Eso por un lado, otro lado es que siempre es un momento cuando todo va un poco más fácil, más flexible, porque cuando ya puedes ir con la botella, además es más bonito para todos.
Sí, por lo menos lo puedo
I just think that's
tener.
economically interesting. I don't know what implications it might have.
Vamos a, sí, a las 8:30. Ok, entonces digo que o se vayan a casa o se quedan aquí un poco para no llegar ahí demasiado.
So this is potentially a simple question, I guess. It's a question of definition. I guess I'm just curious if there's like a good line between a star in a dense cluster or a star in a like wide multiple star system, because wouldn't they both? You know, like how do you set the limits between those two things?
It's difficult. I mean, it's a question. Here is just a question of convention. I think probably if you have a system with a 7-8 stars, and it's quite possible that the central stars of many clusters are like that. You could claim that there are systems of their own, but yeah, normally you have low mass stars around. I mean, you can have a few which are also in the multiple system, but you have other that are going around. Depends on numbers probably.
Okay, from the point of view of n-body interaction and making hard binaries, wouldn't it make more sense to plot the binary fraction and the binary, what do you call period? No, the AU, the period. No, it's not the period. The separation length is too late. It's 8 o'clock. But as function of density, stellar density, because that will help a bit to address. I mean, the concern about how we get the large separations and being clustered and so on. Here, you get the chocolate for being.
Don't eat all of that because you're going to have extra sugar in your body. Yeah, it's probably,
No one has done that.
No, I don't think anyone has.
It is time.
You see, the few systems of which, as you can see in this last plot showed, there are few systems for which we have sensible measurements. And it's difficult. I mean, once you go to these sort of distances, measuring stellar density is, you can measure density of O-type stars, but I don't know if that correlates to O-type star density or not.
Okay. I was gonna close, but you asked the last question of today.
Alright, I had a question about that last image you were looking at with the runaway OB type stars. Are those runaway stars, are they still in binaries? Or are they all on their own now?
That's an interesting question. I mean, in principle, you suppose in most of these interactions, the star that goes away is single. But it's not necessarily the case. In fact, the same student that should have done that massive system that could merge was studying another thing that was driving him crazy, and after lots and lots of hard work, he came to the conclusion that maybe it was essentially we had a similar system with two
the mid-O-type stars, and it had an orbital period from the radial velocities, and an orbital period from the eclipses, and they were completely different. So it came to the conclusion that what you had there was two mid-O-type stars in a very close binary, and two late O-type stars in a close binary, and that they were very far away, orbiting each other. And that's sort of system that exists and is complex. And now Gaia seems to have shown that this thing has been ejected from the center of our cluster. And in fact, if you look at it, you have this system here, and you have an O3 star, which is a very massive star, going in exactly the opposite direction at exactly the same distance, which is very intriguing, I must say, and shows that you can eject even very complex systems. I don't understand how a white binary can be ejected and preserve the geometry, but it seems to happen.
Rainer has the microphone.
I'm okay. If there's any more questions, we're not in a hurry at the moment, so we can still. But I don't want to.
Speak for yourself.
Okay, let's give Ignacio a break, and I also don't want to undermine Angela's authority. As declared, it was the last question. Okay, so let's close this. Thanks a lot to all the speakers. I mean, massive efforts here, I have to say. We have dinner now, free dinner. I'm not free. Now you don't have to pay. It's at the Hotel Vinci Albaicin. I don't know why it's called Albaicin, because it's not on the Albaicin, but it's like these marketing tricks. There's also these hotels that are called center, and they're never in the center. But the good thing is that this is 15 to max 20 minutes walking from here. I'd rather 15 minutes. The thing is that dinner is at 8:30, so we will first have a little reception where you stand and everyone has a beer or wine or something, and then the dinner. You can either go home now and meet us there, or alternatively you can stick around, hang around here, do your emails, look up into the dark sky, do whatever you want, talk, socialize, and then maybe in half an hour I would take you from here walking to the hotel. And if you have any doubts where it is, please let me know, but it's on the web page.
So the reception part starts at 8:30, it's not like at 8?
No, that's the thing. I mean, if you show up now there, they will say, what are you guys doing here?
Okay, so don't show up before.
So the other alternative is you go and have a beer, or several ones already until then, but
several beers in 20 minutes.
I